Hello everyone, so in this video I'm going to discuss properties of matter and fluids. So we're going to see more than 15 problem types which can be asked in JEE Mains 2025, and it's going to be a revision video, but we'll see application of each and every concept. So without any further delay, let's begin the session. Now let us see the first problem type, which is based on elasticity. So we have given assertion as the property of body by virtue of which it tends to regain its original shape when the external force is removed is elasticity. So that is the definition of elasticity, so the assertion is correct. Now the reason is the restoring force depends upon the bonded interatomic and intermolecular force of solid. So the restoring force arises because of the interaction between the atoms and the molecules. So the reason is also correct and it is the right justification for the assertion. So option 3 is the right answer. Now let us see the next question. With rise in temperature, the Young's modulus of elasticity. So Young's modulus decreases with the increase in temperature, so it will decrease. If we have Young's modulus on the y-axis and temperature on the x-axis, so it will decrease because Young's modulus tells us the stiffness of the material, and the stiffness decreases as we increase the temperature. So it should be option 2. Now let us see the next problem type, which is based on Young's modulus. So one end of a metal wire is fixed to the ceiling and the load of 2 kilogram hangs from the other end. So we have given a metal wire which is hanging from the ceiling and there is a load of 2 kilograms suspended from the wire. A similar wire is attached to the bottom of the load and the another load of 1 kg hangs from the lower wire. Now we have attached another wire to 2 kg and on the other end we have attached a mass of 1 kilogram. Then the ratio of the longitudinal strain of the upper wire to the lower wire. So we have to find the strain. Let me call this wire 1, this wire as 2. So longitudinal strain in wire 1, ratio, we have to find the ratio, right? So let me call L1 by capital L1, ratio of L2 by capital L2. Right, so similar wire is given, right? So then area of cross section is also given, Young's modulus is given, both are like steel wire, and G is 10 meters per second square. They are saying similar, so I'm assuming their length is also same, and we have to find the strain. So what we can do, let us find the stress in the first wire. To find the stress in the first wire, we can find the tension in the first wire. So if we draw the free body diagram of this region of these two masses together, they are in equilibrium because of the tension due to the tension developed in the first string. So we can say T1 will be equals to 2 plus 1 times G. G is given as 10, so that will be 30, right? So here I'm ignoring the mass of the second wire because it is very thin and its mass will be negligible in comparison to the mass of the blocks. So this will be 30, and similarly for the second wire, the tension, if you draw free body diagram of 1 kg, the tension in the second string comes out to be 1 into 10, which will be 10 Newton. Now we got the tensions. Now we know Young's modulus is defined as stress upon strain. So strain is defined as stress upon Young's modulus, and stress can be written as the tension in the wire divided by area of cross section. Now we have to find the strain. So strain in wire 1 divided by strain in wire 2 will be T1 by T2, and they have the same area of cross section, and Young's modulus is also same. So it comes out to be 30 by 10, which comes out to be 3. So 3 is the answer of this question. Now that is the next question based on the same problem type. A wire of length L and radius R is clamped at one end. If its other end is pulled by the force, so let us say there is a wire which is clamped at one end and we are pulling this wire with a force F. Its length is given as L and the radius is R. Its length increases by L, so the elongation is given as L. So elongation in the wire is L, small l. So if the radius of the wire and the applied force both are reduced to half of its original value, so we are reducing force to F by 2 and the radius will become R by 2, keeping the original length constant. So we are not changing the original length. The increase in the length will be, so we know that Young's modulus is given as F by A, and then we have small l and then capital L. So from this, if I want to compare and we want to find the increase in length, so the increase in length will be FL upon AY, and area of cross section can be written as pi r square. So from this, we are keeping length constant, so pi is also constant, and we are not changing the Young's modulus. So we can say length is directly proportional to F and inversely proportional to square of the radius. So so what we can do, L2 by L1 will be equals to F2 by F1 and R1 by R2 square. So R2 is R1 by 2 and F2 is F1 by 2. So we know what is F2 by F1, that will be 1 by 2. And R1 by R2 is 2. So that comes out to be 2. So so the new elongation will be 2 times the original elongation, so it will be increase. So here the increase in the length will be 2 times, so it becomes 2 times, right? So option 4 is the right answer. Now let's see this question based on the same problem type. Two metallic wire P and Q have the same volume, are made up of the same material. So when they are saying the same volume, if A is the area of cross section and L is the length, then volume will be area of cross section times the length. Material is also same. If their area, so material is same, it means they must be having the same Young's modulus. If their area of cross section are in 4:1, so we have given AP by AQ as 4 by 1. And force F1 is applied to P and elongation of delta L is produced. So when we apply force F1, so F1 by A times L1 by capital L. So this is given as, so this L1 is nothing but delta L, and that is Young's modulus. Now the force which is required to produce same extension in Q is, so we are keeping extension same. So Y is F by A, L by L. So here Young's modulus is same for both the wire. Right? And we have to find the force. The force will be different. Length and the area of cross section will be different. And force which to produce the same extension. So L is also same. And the length, area of cross section is, so volume is same. So we can say A1 L1 will be equals to A2 L2. So we can say L1 by L2 will be A2 by A1, and A2 by A1 is 1 by 4. Or I can say LP by LQ will be 1 by 4. So length will be different, area of cross section is different, so we have to compare, we have to find the force. So force will be directly proportional to A and inversely proportional to the length. So we can say FQ by FP will be equals to AQ by AP times LP by LQ. Now from this, AQ by AP is 1 by 4 and LP by LQ is 1 by 4. So from this, FQ will be FP by 16, and we have to find, so okay, right, so FQ is F2, right? So F2 by F1 is 1 by 16, so F1 by F2 will be 16. So 16 is the answer of this question. Right, so let us the next question based on the same problem type. Each of the 3 blocks PQ are shown in the figure has the mass 3 kilograms. Each of the wire A and B has cross-sectional area of 0.005 square centimeter, and Young's modulus is 2 into 10 raised to power 11 Newton per meter square. Neglecting friction, the longitudinal strain in the wire B. So here what will happen, since there is no friction, R will go down and P and Q will go in the right direction. Let us say acceleration is A. Okay, so here the weight on R is responsible for the acceleration of the system, right, along the string. So this weight is 30 Newton, right? So we can say 30 Newton divided by the mass of the system, which will be mass of P, Q, and R, and each block has the mass 3 kilograms. So that will be 3 plus 3 plus 3. That will be the acceleration. So 30 by 9. So which comes out to be 10 by 3. So 10 by 3 meters per second square is the acceleration. And we have to find the longitudinal strain in B. And we know that strain is stress upon Young's modulus. Now what is the stress? So let us find the tension T1, right? So if you draw free body diagram of R, so there will be a weight in the downward direction which is 30 Newton. There will be tension T1 in the upward direction. Acceleration is 10 by 3. So we can say 30 minus T1 will be mass times the acceleration. So T1 comes out to be 20 Newton. So we got the tension. So stress can be written as T1 by A1 divided by Young's modulus. Now T1 is 20. Area of cross section is given as 0.005 square centimeter. So 0.005 into 10 raised to power minus 4 in meter squares multiplied with the Young's modulus, which is 2 into 10 raised to power 11. Right? So we can write this as 20 by 2 times 5 into 10 raised to power minus 7 plus 11. So that will be 10. So this will cancel out. So it will be 2 divided by 10 raised to power. It comes out to be 4. So it will be 2 into 10 raised to power minus 4. So 2 is the answer of this question. Now let us do the next question based on the same problem type. So two blocks of mass 2 kg and 4 kg are connected by a metal wire going over a smooth pulley as shown in the figure. The radius of the wire is 4 into 10 raised to power minus 5 meter, and Young's modulus of the metal is 2 into 10 raised to power 11 Newton per meter square. The longitudinal strain developed in the wire is 1 upon alpha pi. The value of alpha is, so here since the I'm assuming the pulley is light, so 4 kg will go down and 2 kg will go up. Let us say acceleration is A, and it's the Atwood machine, and which we have covered in Newton's laws one shot. So here acceleration comes out to be, or tension comes out to be 2 times m1 m2g divided by m1 plus m2. So this will be 2 times 4 times g is 10 divided by 2 plus 4. So it will be 160 divided by 6, or we can say 80 by 3 Newton. So 80 by 3 Newton is the tension, and we have to find the strain. So the strain will be strain will be stress upon Young's modulus, and stress can be written as tension divided by area of cross section. So tension is 80 by 3. Area of cross section can be written as pi times radius is given, right? Square of that 16 into 10 raised to power minus 10. Young's modulus is 2 into 10 raised to power 11. Right? So this can be written as, so we have 4, and this will be 20, and this will give us 5. So it comes out to be 5 divided by 6 pi into 10, and this will be 2. So it will be 1 upon 12 pi. And this is given as 1 upon alpha pi, so alpha will be 12, right? So 12 is the answer of this question. Now let us see the next problem based on the same problem type. An elastic spring under tension of 3 Newton has a length L. If the length is B under tension 2 Newton, for its length 3a minus 2b, the value of the tension will be, right? So let us say the original length original length of the spring is L, and when we exert a force of 3 Newton, the increase in the length let us say is L1. So L plus L1 is given as A when we are exerting tension 3 Newton. Similarly, L plus L2 is given as B when we are exerting force of 2 Newton. And when and let us say it becomes L plus L3, when we are, it becomes 3A minus 2B. When we are exerting a force, that's what we have to calculate, right? Let us say this force is F. So this we have to calculate. So here L1 can be written as FL upon AY, where F will be 3, L is the original length divided by area of cross section times Young's modulus. Similarly, L2 can be written as 2L upon AY, and L3 will be FL upon AY. Right, so now what we can do, let us substitute A and B in the third equation. So this will become L plus L3 is equals to 3 times L plus L1 minus 2 times L plus L2. Okay, so this will be L plus L3 is equals to 3L minus 2L plus 3L1 minus 2L2. So this L will get cancelled out, capital L will get cancelled out. So we are getting L3 as 3L1 minus 2L2. Now what we can do, we can substitute L1, L2 and L3 values in this equation. So this will become FL upon AY is equals to 3 times L1, which will be 3L upon AY minus 2 times L2, which is 2L upon AY. Now L upon AY will be eliminated, so we'll get F is equals to 9 minus 4. So that comes out to be 5. So F will be, so the answer will be 5. Now let us see the next question. A wire of cross-sectional area A and modulus of elasticity 2 into 10 raised by 11 Newton per meter square and length is 2 meter is stretched between two vertical rigid supports. When a mass of 2 kg is suspended at the middle, it sags lower from its original position, making an angle theta which is 1 by 100 radian. So 1 by 100 on the points of the support. The value of A is, so we have to find the area of cross section of the wire, right? So what we can do, so what is this X? Since theta is very small, we can say in this right angle triangle, tan theta is X by L. So since theta is very small, so tan theta can be written as theta. So from this X comes out to be L theta, and length is given, L is 1 and theta is 1 by 100. So we got X value, right? So X will be 10 raised to minus 2 meters. Now let us, we need to find the area of cross section. So we have to use this formula, y is equals to stress upon strain, and stress in this case will be the tension in the wire upon area of cross section divided by strain, and right, so that will be the increase in length upon the original length. So increase in length, let us say, so it will be strain will be 2 times root of x square plus L square minus 2L, right? So that is strain. So let us find the value. So first let us find tension. So tension will be, so if I draw free body diagram of this knot, so we can say there will be a tension in this direction, there will be a tension in this direction, right? And there will be a weight. Now in this string, the tension will be 20 Newton because it is connected with a 20 kilogram block which is at rest. So this will be 20 Newton and this angle is theta. So the horizontal component of the tension will get cancelled out. So vertical components will balance the 20 Newton. So we can say 2t sine theta will be equals to 20, or 2t, and sine theta can be written as theta, which is 1 by 100 because theta is very small. Now from this tension comes out to be 1000 Newton. So we got the tension. Now let us find the strain. Strain will be 2 times root of x square plus L square minus 2L, right? Because the length of the string is 2L and this hypotenuse is root of x square plus L square, and twice of that will be the new length. So this will be divided by the original length. So from this, let us take L common, and L, so 2L is equals to 2, so L is nothing but 1. So we can make L as 1. So it will be 2 times. So 2 will get eliminated. Root of x is x square will be 10 raised to power minus 4. L is 1 minus 1 divided by 1. So this can be written as, so we can apply binomial approximation. So root of 10 raised to power 4 plus 1 can be written as 1 plus 1 by 2 times 10 raised to power minus 4 minus 1. So this will get cancelled out. So it will be 5 into 10 raised to power minus 5. So we got the strain. So this can be written as 1000 divided by A, and the strain is 5 into 10 raised to power minus 5. Young's modulus is given as 2 into 10 raised to power 11. So from this, area of cross section will be 10 raised to power 3 divided by 5 into 10 raised to power minus 5 divided by 2 into 10 raised to power 11. Now from this, it will be 10 raised to power 3 plus 5 minus 11 minus 1. So which comes out to be 10 raised to power 8 minus 12, or 10 raised to power minus 4. So that is the area of cross section. So the answer will be 1. Okay, let us see the next question. Two persons pull a wire towards themselves. Each person exert a force of 200 Newton on the wire. Young's modulus of the material is given as 10 raised to power 11 Newton per meter square. Original length of the wire is 2 meter. This is Young's modulus. This is the force. And the area of cross section is 2 centimeter square. So that is area. So wire will extend in length. So on the wire there is a force of 200 Newton in the left direction, 200 Newton in the right direction. So we can say the restoring force will be nothing but 200 Newton. So F will be 200 Newton. So let us apply Young's modulus formula. So that will be F by A, and then we have capital L by small l, where small l is the elongation. So small l will be FL upon A by. F is 200, length is given as 2 meters, area of cross section is given as 2 into 10 raised to power minus 4 in meter square, and Young's modulus is 10 raised to power 11, so 2 will get cancelled out. So that will be 2 into 10 raised to power 2 plus 4 minus 11, and we have to find answer in micrometer. So that will be 2 into 10 raised to power 6 minus 11, that will be minus 5. So divide by 10 multiplied with 10, so that will become 20 micrometers. So 20 is the answer of this question. Right, so let us see this question. Young's moduli of material of wire A and B are in 1:4. So YA upon YB is given as 1 by 4, while its area of cross sections are in 1:3. Area of cross section is 1:3. The same amount of load is applied to both the wire. So F1 is equals to F2. The amount of elongation produced in the wire A and B will be in what ratio? So we know that the elongation is FL upon AY, and here for both the wire we are exerting same force, and they are made of right, and assuming length of the wire to be same, so their length are also same, and we have to find the amount of elongation. Same amount of load applied on both the wire. Yes, so now what we can say, the elongation will be inversely proportional to area of cross section and Young's modulus. So LA upon LB will be AB YB upon AA YA. So that will be AB upon AA is 3, whereas YB upon YA is 4. So this comes out to be 12. So the answer will be 2. Right, so now let's see the next question. Young's modulus of steel wire of length 6 meter and cross-sectional area 3 square millimeter is 2 into 10 raised by 11 Newton per meter square. The wire is suspended from its support on a given planet. Right, so it is suspended from a support. A block of 4 kg is attached to the free end. So there is a block of mass 4 kilograms attached. The acceleration due to gravity on the planet is 1/4 of its value on the earth. The elongation in the wire. So here the weight will be 4 times the value of G at that planet, which is 1/4 of the value on the earth. So this will be 4 times G by 4. So that will be G, and G is 10, right? So 10 Newton force is acting in this case. So the tension will be 10 Newton. And we have to find the elongation. So L will be T L upon AY, and tension is 10. Length is 6 meters. Area of cross section is 3 into 10 raised per minus 6. Young's modulus is 2 into 10 raised per 11. So 6 will get eliminated. So that will be 10 raised per 1 plus 6 minus 11. So that will be 10 raised to per minus 4. And we have to find answer in, okay, right? So this is nothing but this is in meters, right? So if I multiply this with 1000, we'll get answer in millimeters. So that will be 0.1 millimeter. So option 3 is the right answer. Let us see this question. The area of cross section of the rope used to lift a load by a crane is 2.5 into 10 raised per minus 4 square meter. The maximum lifting capacity of the crane is 10 metric ton. So it can lift 10 tons. So 10 tons will be 10 into 10 raised per 3 kilograms. To increase the lifting capacity of the crane to 25 metric tons, so we want to lift 25 into 10 raised per 3 kilograms. The required area of cross section of the rope will be, so we want to increase the lifting capacity, so we can say this will be, if I multiply this with G, let us multiply this with G, so that will be you can say F1 and this will be F2, right? So we got the force and we have given area of cross section in the first case. So A1 is given as 2.5 into 10 raised per minus 4. Right, so if we exceed stress beyond a from this value, it will break. So here area of cross section is A2. So let us write down the formula. Y is equals to FL upon AY. So here I'm assuming L is same. There is no change in the length. So length will be constant. They are made of the same material. So I'm treating Young's modulus to be same. And force is different. So area of cross section will be different. Young's modulus will be same. So I'm assuming same material. So in this case, force will be directly proportional to the area of cross section. So we can say so we can say A2 by A1 will be equals to F2 by F1. So A2 will be A1, which is given as 2.5 into 10 raised per minus 4. F2 will be 25 into 10 raised per 4 divided by 10 into 10 raised per 4. So it comes out to be 6.25 into 10 raised per minus 4 square meter. So option A is the right answer. Okay, a steel wire of length 3.2 meters, Young's and the Young's modulus is 2 into 10 raised by 11 Newton per meter square, and a copper wire of length 4.4 meter, Young's modulus is 1.1 into 10 raised by 11 Newton per meter square. Both of the radius 1.4 millimeter are connected end to end. When stretched by the load, the net elongation. So when we are connecting a wire end to end, the tension we can assume same in both the wire. When stretched by the load, the net elongation is found to be 1.4 millimeter. The load applied in Newton will be. So we can say the elongation in steel plus elongation in copper will be the net elongation, right? And this net elongation is given as 1.4 into 10 raised per minus 3 meters. So the elongation in steel can be written as F, length will be 4.4, FL upon AY. Sorry, length is 3.2. Area of cross section, so pi r square, so pi r in this length, both have same radius, right? So it will be pi r square, and Young's modulus is 2 into 10 raised per 11 plus F into 4.4 divided by pi r square times Young's modulus, which is 1.1 into 10 raised per 11, and this is given as 1.4 into 10 raised per minus 3. Now in this equation we have only F is unknown to us, so let us simplify this, and pi we have to take as 22 by 7. So this will give us 1.6. R is given as 1.4 millimeter. So it will be F, let me take F as common. So 1.6 divided by 22 by 7 times 1.4 times 1.4 times 10 raised to power minus 6 plus 11. Right, so this will give us 0.2, this will give us 8, and 4 and 11, 2 and 0.7, plus this will be 4. So 4 divided by 22 by 7 times 1.4 times 1.4 into 10 raised to power minus 6 plus 11. So that will be 0.2. This will be 20, 10, this will be 11. Right, so this comes out to be 1.4 into 10 raised to power minus 3. So let us simplify this. So this will be 2 divided by 11 into 10 raised to power 5, and we have 0.7 also, right? So 10 raised to power 5 plus 10 divided by 1, 15.4 into 10 raised to power 5 is 1.4 into 10 raised to power minus 3. Right, so from this we can take 10 raised to power 5 on the other side, and 0.77. Okay, right, so we got that. So it will be 2 divided by 0.77, sorry, 7.7, and here we have plus 5 divided by 7.7 times F, and that will be 1.4 into 10 raised to power 2. So let us take this 7.7 on the other side. So we got F as 1.4 into 7.7 by 7 into 10 raised to power 2. So that will be 0.2. So it comes out to be 154. Right? So F comes out to be 154. So option D is the right answer. Right, so let us see the next question. Given below are two statements. Assertion is given as steel is used in the construction of buildings and bridges. That is correct. That is fact. Reason steel is more elastic and its elastic limit is high. So reason is the correct justification for the assertion. So option 3 is the right answer. Now let us see the next problem type, which is based on to find the equivalent Young's modulus. So two wires of same length and radius are joined end to end. So there are two wires and the same length and radius. So this is wire 1 and this is another wire. So this length is L and this is also L, and area is pi r square. Young's modulus is given y1 and y2, and the combination behaves as a single wire, then its Young's modulus will be. So if we consider this made of a same material, in that case the length will become 2L, area of cross section will be same, pi r square, right? So what we can say, y equivalent will be, and we are exerting for some force, so F upon A and the elongation. Okay, right, so let us first find the elongation, right? So I'm assuming the same elongation in both the cases. So here elongation will be F L upon A Y. So in this case elongation will be L1 plus L2, which will be F L upon A Y1 plus F L upon A Y2, right? And this is nothing but F times 2L by AY, right? Because this will be equals to L only, right? Because we are considering the equivalent length. Right, so elongation will be same in both the cases. So from this 1 by y1 plus 1 by y2 will be equals to 2 by y. So y comes out to be 2 y1 y2 upon y1 plus y2. So option 2 is the right answer. Okay, right. So a stone of mass 20 grams is projected from a rubber catapult of length 0.1 meter and area of cross section is 10 raised per minus 6 square meter. So it is based on the equivalent spring constant, right? So the equivalent spring constant will be, so if I write F can be written as y a by L times the elongation. Now this y a by L is nothing but the effective spring constant. So stone of mass 20 grams projected from the rubber catapult of length 0.1 meter and the area of cross section is 10 raised per minus 6 and stretched by the amount of 0.04 the velocity of the projected stone. So what is happening, the potential energy stored in the catapult will get converted into the kinetic energy of the stone. So we can say half mv square will be equals to half k L square, right? So half will get cancelled out. Mass is given as 20 by 1000. V square Young's modulus is 0.5 into 10 raised per 9. Area is given as 10 raised per minus 6. Length is given as 0.1 and the elongation is given as 0.04. So 16 into 10 raised per minus 4. Now from this, this will be 10 and 8. So we can say V square will be 0.5. Okay, let us remove this. So 5 into 8 into 10 raised per 9 minus 6 minus 4 plus 2. So that comes out to be 40 into 10 raised per that will be 10 minus 10 minus 1. So this will be 1, right? 11 minus 12 11 minus 10 will be 1. So V comes out to be 20. So 20 is the answer of this question. Right, so next question is based on vertical circle. Basically there will be a wire which is attached with the mass and then they will ask us what is the elongation in the wire when the block is at the bottommost position. A string of area of cross section 4 square millimeter and length 0.5. Length is, so unit is not given, I'm taking it as meter, right? Is connected with a rigid body of mass 2 kg. The body is rotated in a vertical circular path of radius 0.5. So there is a mass of 2 kg which is attached with a string which is having an area of cross section 4 square millimeter, length is 0.5, mass is m, right? So this mass is connected is 2 kg. The body is rotated and the radius is given as, so the length of the string is 0.5, right? So length, this is L only, right? The body acquire a speed of 5 meters per second at the bottom of the circular path. The strain produced in the string when the body is at the bottom of the circular path is dash times 10 raised to the minus 5. So we have to find the strain, right? So here Young's modulus is given, G is given. So in this question, first we have to find the tension and then we'll apply Y is equals to stress upon strain, and from that we can find the strain. So so stress will be, so let us draw the free body diagram as the mass is going in a circular path. So at the bottommost point, if I draw free body diagram, so there will be a gravitational force of 20 Newton in the downward direction and there will be a tension in the upward direction, and it is having a velocity of 5 meters per second at the bottommost position. So the centripetal force will be T minus 20 and that will be V square by R. Mass is given as 2, V is 5, so 25, R in this case is given as 0.5. So T comes out to be 20 times 50 plus 50 times 2. So that will be 120. So the tension will be 120 Newton. So the strain will be stress, that is 120 divided by area of cross section 4 into 10 raised per minus 6 divided by the Young's modulus which is 10 raised per 11. Now from this I am getting 30 into 10 raised per 6 minus 11. So it will be 3 into 10 raised per minus. This is minus 5. Now 30 into 10 raised per minus 5. So answer will be 30. Right? Now let us see the case of a horizontal circle. A wire of length 50.5 meter and cross-sectional area 10 raised per minus 4 square meter has a breaking stress of 5 into 10 raised per 8 Newton per meter square. A block of 10 kg is attached at one end of the string and is rotated in a horizontal circle. The maximum linear velocity of the block without breaking the wire. So it is moving in a horizontal circle and breaking stress is 5 into 10 raised per 8. So the stress is given as strain times the Young's modulus. And we have to find the maximum linear velocity. So the tension will be nothing but the centripetal force, and that will be mv square by r. So it will be m v square by l. M is given as 10, length is given as 0.5, and we have to calculate. So that comes out to be 20 v square. So tension will be 20 v square. So stress will be 20 v square upon area of cross section, which is 10 raised per minus 4. Strain, okay, right. Breaking stress is given. Okay, right. So breaking stress is given. So no need to apply this formula. So that is not required. So we got the stress. And stress is given as 5 into 10 raised per 8. So it depends upon, so V depends upon the stress. Greater the stress, greater the speed. So for maximum speed possible will be, will get the maximum value when the stress is maximum, right? Which is 5 into 10 raised per 8. So from this, this will give us 4. So V square will be 1 by 4 into 10 raised per 4. So V will be 100 by 2. So that will be 50 meters per second. So 50 is the answer of this question. Right. So let us see the next concept, which is based on shear stress. A square aluminium slab. So shear modulus is 25 into 10 raised per 9 Newton per meter square. Of side 60 centimeter, thickness 15 centimeter, is subjected to a shearing force on its narrow face. So what do you mean by that? It's a square sheet. So we are exerting shearing force on this surface, right? Thickness is 15 centimeter. So this thickness is 15 centimeter. Length is 60 centimeter. And this force F is 18 into 10 raised per 4 Newton. The displacement of the upper edge. So due to this, the upper edge will displace with respect to the bottom edge. Like this, right? So this displacement is x. So we know that modulus of rigidity is equals to F divided by, F is the force and A is the area of the face on which we are exerting the force, divided by x by L, where L will be this length, right? And this length will be 60 centimeter. So it will be F by x, L by A, and we have to find the displacement. So x will be FL upon eta times A. So F is 18 into 10 raised per 4, L will be 0.6, divided by eta is given as 25 into 10 raised per 9, and area of cross section of the topmost face where we are exerting the force will be 0.6 times 0.15 meter. So let us simplify this. 0.6 will get cancelled out, and let me remove this decimal. So this will become 10 raised by 2. So this will give us 4, and this will be 5, and this will be 6. So we are getting 4.8 into 10 raised per minus 5, or we can write this as 48 into 10 raised per minus 6 meter. So that will be 48 micrometer. So answer will be 48. Right, so let us see the next problem type, which is based on bulk modulus. If average depth of the ocean is 4000 meter and the bulk modulus of water is 2 into 10 raised per 9 Newton per meter square, so that is bulk modulus and that is the depth. Then the fractional compression of water at the bottom of the ocean is alpha times 10 raised per minus 2. The value of alpha is. So we know that bulk modulus is defined as the excess pressure divided by the fractional change in the volume. So excess pressure in this case will be rho gh minus delta V by V, and we have to find delta V by V, right? Compression. So rho gh divided by V. So density is given as 1000 and G. So I'm assuming like there will be a change in the density, but for to calculate the excess pressure, we can assume density to be constant. So G is given as 10, H is 4000, and bulk modulus is given as 2 into 10 raised to power 9. So it comes out to be 2 into 10 raised to power 7 minus 9. So that will be 2 into 10 raised to power minus 2. Right? So, and this is given as alpha into 10 raised to power minus 2. So alpha will be 2. Right. So let us see the next question based on the same problem type. The depth below the surface of sea at to which a rubber ball to be taken so that to decrease its volume by 0.02%. So delta V by V into 100 is given as 0.02%, right? So we can say delta V by V can be written as 2 into 10 raised to power minus 4. And we have to find the depth. So we can say delta P divided by minus delta V by V. Let me put a negative sign here. Will be equals to bulk modulus. So excess pressure can be written as rho gh divided by minus delta V by V equals to bulk modulus, and H we have to calculate. So it will be B times minus delta V by V divided by rho G. Bulk modulus is given as 9 into 10 raised to power 8, and bulk strain is 2 into 10 raised to power minus 4, which we have calculated, divided by density is 1000 and G is 10. So this will give us 18 into 10 raised to 18 only, right? 18 into 10 raised to power 6 minus 6, or 4 minus 4, sorry, 4 minus 4, so that is nothing but 18. So 18 meter is the answer of this question. Right, so let us see the next question. So here we have to match the columns. So a force that restores an elastic body of unit area to its original state. Unit area to its original state is known as the, like, it will be the restoring force. So here we can say they're talking about the stress. So force per unit area will be nothing but the stress. So A corresponds to 3. Two equal and opposite forces parallel to the opposing phase. So they're talking about the shear. In shear, what is happening? So if we are exerting a force in this direction, there will be a force exerted by the ground in the left direction if we have fixed the bottom face. So B corresponds to shear. So that will be 4. Right. So A3, B4, force perpendicular everywhere to the surface per unit area, same everywhere. So if we consider a body and we are exerting force per unit area, so we can say the pressure is same. So they're talking about bulk modulus, right? So C corresponds to 1. Two equal and opposite forces perpendicular to the opposing faces. So if we have a rod and we want to elongate this, so we are exerting forces normal to the faces, right? Normal to the area of cross section. So this will be Young's modulus. So D corresponds to 2. So option 2 is the right answer. Right, so the next problem type is based on the elongation rod due to its own weight. A uniform heavy rod of mass 20 kilograms, cross-sectional area 0.4 square meter and length 20 meter is hanging from the fixed support, neglecting the lateral contraction. The elongation in the rod due to its own weight is x into 10 raised to minus 9 meter. The value of x is, right, so when there is a rod, which is getting elongated under its own weight. So in that case, the elongation is given as mgl upon 2ay. So we can remember this. So where m is the mass, so 20, g is 10, length of the rod is 20 upon 2, area of cross section is 0.4. Young's modulus is 2 into 10 raised per 11. So we are getting, this will come 10, 10. So it will be 2.5 into 10 raised per 3 minus 11. So 2.5 into 10 raised to per minus 8. So which is 25 into 10 raised per minus 9. So that should be the elongation. So answer will be 25, right? So let us see another question. So the density and the breaking stress of a wire is 6 into 10 raised per 4 kilogram per meter cube and 1.2 into 10 raised per 8 Newton per meter square respectively. The wire is suspended from the rigid support on a planet where acceleration due to gravity is 1/3 of the value on the surface of the earth. The maximum length of the wire with without breaking, it should be without breaking, right? Without breaking is, so that what we have to calculate. So since we have suspended the rigid rod on the planet, so here they are talking about, so we have to consider that it is getting elongated under its own weight. And we know that if a wire is getting elongated under its own weight, wire of length L, then the elongation is given as mgl upon 2ay. So this what we have to use. So here the strain L by capital L will be mg upon 2ay, and the strain can be written as stress upon Young's modulus, and stress we have given as 1.2 into 10 raised per 8 upon Young's modulus. So this will be, mass can be written as density times the volume, and the volume will be area of cross section times the length. G, and G in this case will be G effective will be G by 3 upon 2 ay. So a will get cancelled out, Young's modulus will get cancelled out. Now from this we can find L. So 1.2 into 10 raised per 8 times 2 divided by density, which is 6 into 10 raised per 4. G is 10 multiplied with 3. So that should be L, right? So let us simplify this. So it comes out to be, this will be 3, this will cancel out. So it comes out to be 1.2 into 10 raised per 8 minus 5. So L will be 1200 meter. So this should be the answer, but NT has given answer as 600 Newton because they have considered that instead of mg by 2, they have taken it as mg, right? So which is incorrect. It should be 1200. Right, so let us see the next question. An aluminum rod of Young's modulus 7 into 10 raised per 10 Newton per meter square undergoes elastic strain of 0.04%. The energy per unit volume stored in the wire. So here this is the energy density. So energy density is defined as half times stress times strain. So you can remember this energy density. And if you want to find the potential energy, that will be, potential energy will be half times stress times strain times volume, where volume is area of cross section times the length. So this is energy density and this is potential energy stored in the stretched wire. An aluminum rod with Young's modulus. So we have given strain and we have to find the energy density. Energy per volume is energy density. So it will be half times stress times strain. Since strain is given, we can write stress in terms of strain, which will be Young's modulus times the strain. So that will become strain square. So half Young's modulus is 7 into 10 raised per 10. Strain is 4%. Or you can say, so strain will be 4 into 10 raised per minus 4. square of that. So this will become 16 times 7 by 2 times 10 raised power 10 minus 8. So it will be 56 into 10 raised power 2. So 5600 will be the energy density. So option 1 is the right answer. Now the next problem type is based on stress strain graph. So as shown in the figure, in an experiment to determine Young's modulus of a wire, the extension load curve is plotted. The curve is straight line passing through the origin and makes an angle of 45 degree with the load axis. The length of the wire is 62.8 centimeter and its diameter is 4 millimeter. So length is given as 62.8 centimeter, or we can write this as 2 into 3.14 times 10 centimeter, or you can write this as 20 pi centimeter, right? So that is the length, and its diameter is 4. So diameter is 4 millimeter. Young's modulus is found to be x into 10 raised to power 4. So we have to find the value of x. Now from this, we know that elongation is FL upon AY, right? So that is the formula. Now if I take 2 points on this curve, right? So we can say that will be the increase in the elongation and that will be the increase in the load, right? So from this we can find delta L upon delta F, which will be nothing but tan 45 degree. So we can find the slope, which is nothing but 1. So in this equation, if I take the change, so delta L will be delta F times L upon AY, and delta L by delta F will be L upon AY. Length is given as 20 pi into 10 raised to power minus 2. Area of cross section will be pi into, and D is 4 millimeters, so radius will be 2 millimeters, so 4 into 10 raised to power minus 6. And the Young's modulus we have to calculate. So this is 1. Now from this, Young's modulus will be, so pi will get eliminated. So this will give us 5. So Young's modulus will be 5 into 10 raised to power 4. So 5 is the answer, right? Another question based on stress strain graph. So on the x-axis we have given stress, on the y-axis we have given strain. The elastic behavior of the material for a linear stress strain, linear stress and linear strain is shown in the figure. The energy density for the linear strain is 5 into 10 raised to power minus 4. Linear strain is 5 into 10 raised to minus 4, and we have to find the energy density. Assume that the material is elastic up to the linear strain of 5 into 10 raised to power minus 4. So when the, okay, right, so it is elastic, so we can assume linear relation. So here, first from the stress strain graph, let us find the Young's modulus. So you can take any 2 points. So I'm going to take this point and this point. So that will be stress, and this will give us strain. So we can say stress upon strain will be 80 minus 20 divided by, because the slope will give us the Young's modulus. 80 by 20, 80 minus 20 divided by 4 minus 1 into 10 raised to power minus 10. So it will be 60 by 3 into 10 raised to power 10. So that will be 2 into 10 raised to power 11 Newton per meter square. So we got the Young's modulus, which is stress upon strain, and energy density is we have to calculate, and strain is given to us. So energy density will be half into stress into strain, right? So here strain is given and stress can be written as Young's modulus times the strain. So we got half into Young's modulus times strain square, so half times 2 into 10 raised to power 11, and the square of the strain 25 into 10 raised to power minus 8, because strain is given to us. So this will give us 25 into 10 raised to power 3 joules per meter cube, which is 25 kilojoules per meter cube. So 25 is the answer of this question. Another question based on stress strain graph. So here on the y-axis we have given extension and load ratio, and on the x-axis we have given length of the wire. So in an experiment to determine the Young's modulus, steel wire of 5 different lengths, 1, 2, 3, 4 and 5 meters, but of the same cross-sectional area, 2 into 10 2 millimeter square were taken, and curve between extension and load were obtained. The slope of the curve were plotted with the wire length, and the following graph is obtained. If the Young's modulus of the given steel wire is x into 10 raised to 11, then the value of x is. So here we know that Young's modulus is FL upon A times small l, right? Where small l is the elongation. So here extension is the elongation, load is F, right? So here we have the, so if I take the slope of this, let us, this angle is theta. So tan theta will be delta y by delta x. So delta y will be 1 minus 0.25 into 10 raised to power minus 5. Okay, let me write it somewhere here. So I think this is not visible to you. So let me write here. So tan theta will be delta y by delta x, and it will be 1 minus 0 minus 0.25 times the multiplier, which is 10 raised to power minus 5, divided by delta x, which is 4 minus 1. So this comes out to be 0.75 by 3 into 10 raised to power minus 5, or we can write this as 0.25 into 10 raised to power minus 5. And this is nothing but L by F times L, right? Because on the y-axis we have L by F, on the x-axis we have capital L, right? So y times A will be FL upon L. So this is nothing but 1 upon 0.25 into 10 raised to power minus 5. Now from this data, Young's modulus will be 1 upon 0.25 into 10 raised to power minus 5 times the area of cross section. Area of cross section is 2 into 10 raised to power minus 6. So that will be 1 upon 0.5 times 10 raised to power 11, or 2 into 10 raised to power 11. So 2 is the answer of this question. So the next problem type is based on the relation between Poisson's ratio and the modulus of elasticities. So here what you have to remember, that the relation between Young's modulus, modulus of rigidity and the Poisson's ratio is given by this relation. So here it is not negative, it is plus, right? So 1 plus sigma. Whereas the relationship between Young's modulus, bulk modulus and Poisson's ratio is given by this relation, which is y equals to 3b times 1 minus 2 sigma. Now we're going to use these two equations to find the answer of this question. Right, so the proof of this is not in JEE syllabus. So what you can do, you'll study this about this in detail in your college, right? Just remember these two equations. So here we have to find Poisson's ratio in terms of modulus of rigidity and the bulk modulus. So here basically we have to eliminate Young's modulus, so we can equate both the equations. So we can say 2 eta times 1 plus sigma, and I'm taking bulk modulus as k, as that is which is given in the question. So that will be 3k times 1 minus 2 sigma. Now from this, let us club terms which contain sigma. So I'm taking this term on the left side, so we'll get 2 eta plus 6k times sigma is equals to 3k minus 2 eta. So sigma comes out to be 3k minus 2 eta divided by 6k plus 2 eta. So if we compare this, so option 1 is the right answer. Now let us say another question based on the same concept. Again, it is plus. If y, k and eta are the values of Young's modulus, bulk modulus and the modulus of rigidity of any material, choose the correct relation. So we have to find the relation, right? So basically we have to eliminate sigma. So let us eliminate. So we can say y by 2 eta minus 1 will be sigma, and y by 3k, I'm taking b as k, minus 1 will be minus 2 sigma. Okay, so or we can say sigma can be written as 1 by 2 minus y by 6k. Now let us equate this equation and this equation. So this will become y by 2 eta minus 1 is equals to 1 by 2 minus y by 6k. Okay, right, let us take this negative on the right side. So we have y by 2 eta is equals to 3 by 2 minus y by 6k, and let us divide throughout by y. So we get 1 by 2 eta is equals to 3 by 2 y minus 1 by 6k, and we can also eliminate 2, so we are getting 3 here. Okay, right, so in first option we have given y in terms of other modulus of elasticities. So let us find y. So 3 by y will be 1 by eta plus 1 by 3k. Now from this we are not getting this because there is a negative sign, so 1 is not correct. Now let us find okay, let us simplify this. So that will be 3k plus eta divided by 3k eta, or we can say y will be 9k eta divided by 3k plus eta. So that is also incorrect. Let us find k. So if we find k, so we can write this as 1 by 3k is equals to 3 by y minus 1 by eta. So this will be 3 eta minus y upon y eta. Now from this k comes out to be so this is 1 by 3k, right? So it will be y eta upon 9 eta minus 3y. Yes, so we are getting option 4 as the right answer. So do remember these two equations, right? You will be able to solve such questions. Right, so the next problem type from fluids, the first problem type is from the variation of pressure with depth. So mercury is filled in a tube of radius 2 centimeter up to the height of 30 centimeter. Find the force exerted by the mercury on the bottom of the tube is, so there is a tube which contains mercury, and this height is given as 30 centimeter. Radius of the tube is given as 2 centimeter. So we know that the pressure, and we have to find the force exerted. So what is the pressure at A? So we have given atmospheric pressure. So pressure at A will be atmospheric pressure plus rho GH, rho of mercury, G and H, and H is 30 centimeter, G is 10, and rho is given as 1.36 into 10 raised to power 4. So first let us find the pressure. So 10 raised to power 5 plus 1.36 into 10 raised to power 4, G is 10, H is 0.3. Now from this we get 1 plus 1.36 times 0.3 times 10 raised to power 5. Or I can write this as 1 plus 18, 10, 4. So that will be 1.408 into 10 raised to power 5 Pascal. So we got the pressure at the bottom. So what is the force? So force will be area times the pressure. So area is pi r square, so it will be 22 by 7. Radius is given as 2 centimeters, so 4 into 10 raised to power minus 4 times the pressure. So 1.408 times 10 raised to power 5. So let us simplify this. So this will give us, and we have to find the force. Okay, let us calculate that. So 1.408 times 22 times 4 divided by 7. So I'm getting 17.7 into 10 raised to power 1. So which is 177, right? So 177 Newton is the answer of this question. Okay, let us see the next question. The pressure acting on a submarine is 3 into 10 raised to power 5 Pascal at a certain depth. If the depth is doubled, the percentage increase in the pressure acting on the submarine would be. So we know that pressure increases linearly with depth. When the submarine is at A, so the pressure at A will be P naught plus rho GH. And when depth is doubled, so at B, pressure will be P naught plus rho G2H. Right, and we have to find the percentage increase in the pressure. So delta P upon P, that what we have to calculate. And the pressure acting on the submarine is 3 into 10 raised to 5 at a certain depth, where PA is given as, and this will be P, right, into 100. So that will be the percentage increase in the pressure. PA is 3 into 10 raised to power 5 Pascal. So this can be written as pressure at B minus pressure at A divided by pressure at A times 100. Pressure, so the difference will be, so P naught will get cancelled out, so that will be nothing but rho GH divided by 3 into 10 raised to power 5. And atmospheric pressure is 10 raised to power 5. So we can say P naught plus rho GH is 3 into 10 raised to power 5. So rho GH will be 3 into 10 raised to power 5 minus 10 raised to power 5. So that will be 2 into 10 raised to power 5. So this rho GH is nothing but 2 into 10 raised to power 5. So from this we are getting 2 by 3 times 100. So that will be 200 by 3%. So option 1 is the right answer. Right, so let us see the next problem type, which is based on pressure variation in a rotating closed tube filled with fluid. So here we have given a tube of length 50 centimeter is filled completely with incompressible liquid of mass 250 grams and closed at both ends. The tube is then rotated in a horizontal plane about one of its ends with a uniform angular velocity, which is x into root f. If F be the force exerted by the liquid at the other end, then the value of X will be. So, so we have a closed tube, right? So there is a closed tube which is rotating in a horizontal plane. With a constant angular velocity omega. Now, in this case, the pressure will be variable inside the tube. So, and it has some fluid, some liquid, and the mass of the liquid is given as 250 grams. So if I consider an element which is located at a distance x, and the length of this element is dx. Now this element is rotating in a circular path, so there has to be a centripetal force, and that force will be exerted by the pressure, right? So there has to be a pressure variation on the left side and the right side of this element. So let us say on the left side the pressure is P, so the force will be P times the area, and on the right side pressure has to be more, only in that case we'll get a centripetal force. It should be P plus dP times the area. So it is experiencing a force, this element is experiencing a force of dp times a. So dp times a is the force, and that will be the centripetal force. So dm is the mass of this element, radius is x omega square. So that is the centripetal force. Now dm can be written as total mass of the liquid divided by the length of the column, which is zero 0.5 meters, multiplied with the length, which is x. Right? So we'll get the multiplied with dx. Sorry, dx is the length of this element. Mass per unit length times the length, right? So this will become, mass is given as 2.250 grams, so 0.25. 0.25 upon 0.50 x dx omega square dp times area of cross section. Right, so yes, so we got the force, and we have given that this force is x times root f. So we have dm x mr omega square. So let us simplify this. So this will be 2. So we're getting x by 2 omega square dx. So dp times a. Now what is the force experienced at the right end? So we can find that. So from this we can find the pressure variation. So let me take this a on the other side. So let us integrate this. So at the left end the pressure will be nearly 0, and let us say at the right end the pressure is p. So pressure is varying from 0 to p, as x is varies from 0 to the length. So we can say p will be equals to omega square by 2a will come out of integration, and the integration of x will be x square by 2. So that will be L square by 2, and L in this case is 0.5. So this will be omega square by 2a times 0.5 square by 2. So this is the pressure. So what is the force experienced on the right end? So force exerted by the fluid on the right end will be pressure times the area of cross section. So PA will be omega square 0.5 square divided by 4, and and this force is given as x times root f. So we have to find, so if f be the force and the angular velocity is x times root f, so omega square is nothing but x square times f. So x square times f is 25 into 10 raised to power minus 2 divided by 4 is x times root f. Sorry, this force is not x times root f. Omega is this, right? So we have to find the, oh, this is force, right? F. So f will get cancelled out. So from this we have to find x. So x will be 25 by 400, root of 25 by 400, which is 5 by 20, which is 1 by 4. And the value of x, sorry, this is 1 by x, right? So 1 by x will be 1 by 4. So x comes out to be 4. So 4 is the answer of this question. Right, so let us see the next problem type, which is based on Pascal's law. So here, a hydraulic press containing water has two arms with diameters as mentioned in the figure. A force of 10 Newton is applied on the surface of water in the thinner arm. The force required to applied on the surface of water in the thicker arm to maintain equilibrium. So in case of a hydraulic lift, what we can write, F1 by A1 will be equals to F2 by A2. So here, let me call this as F1, and here we have given diameter, right? So this will be D1 and this will be D2, and we have to find F2. So f1 is 10, area will be pi d square by 4, d1 square by 4, that will be 1.4 square by 4, and f2 we have to calculate, and a2 will be pi 14 square by 4. So pi will get cancelled out, 4 will get cancelled out. So we can say f2 will be 14 upon 1.4 square times 10, so which will be 1000. So it comes out with 1000 Newton. Right, so next question based on Pascal's law. A hydraulic automobile lift is designed to lift a vehicle of 5000 kilograms. The area of cross section of the cylinder carrying the load is 250 square centimeter. The maximum pressure the smaller piston would have to bear. So here we have a smaller piston, and let's say there is a larger piston, right? And the largest piston, we are supporting a vehicle which is having a mass of 5000 kilograms, and the area of cross section of the cylinder carrying the load. So here the area of cross section is 250 square centimeter, and we have to find the maximum pressure the smaller piston would have to bear. So the pressure, so the increase in pressure just below the bigger piston by the weight of the vehicle will be 5000 times 10 divided by area of cross section, that will be 250 into 10 raised per minus 4. So this will give us 2 into 10 raised per 6 Pascals, right? So the same pressure will get transmitted everywhere as per the Pascal's law. So the lighter piston will experience a pressure of 2 into 10 raised per 6. So option 3 is the right answer. Right, so next question is statement 1, pressure in a reservoir of water is same at all points at the same level of water. So that is correct. That is as per Pascal's law, pressure at the same level in a fluid in hydrostatic case is equal. So statement 2, the pressure applied to enclosed water is transmitted in all direction equally. Again, it is another definition of Pascal's law. So both the statements are correct. So option 2 is the right answer. Next question based on hydraulic press. A hydraulic press can lift 100 kilograms when a mass of m is placed on the smaller piston. So here we have a smaller piston, here we have a bigger piston, and this is smaller piston and this is the bigger one. So hydraulics can lift 100 kilograms. So if we have 100 kilograms here, and if we place a mass m here, then we are able to lift 100 kilograms. It can lift how many kgs when a diameter of the larger piston is increased by 4 times, and that of the smaller piston is decreased by 4 times. Now the diameter, so let me call this diameter as d2 and this diameter as d1. Now d2 will become 4 times of d2 and d1 will become d1 by 4, and we are using the same mass. So earlier we can say mg by pi d1 square by 4 is equals to 100 g by pi d2 square by 4, right? So from this pi will get cancelled out, so we can say g will get cancelled out. So m is nothing but d1 by d2 square times 100, right? Now we have changed the diameters, so we can say mg divided by pi d1 by 4 square by 4 is equals to, say, x g by pi d2 times 4 square by 4. So this will get cancelled out. So we are getting, so g will get cancelled out. So m times 16 divided by d1 square times 16 times d2 square is equals to x, and m is d1 by d2 square times 100. So d1 by d2 square times 100 times 256 times d2 by d1 square. So this will get cancelled out. So we are getting x as 25600 kilograms. So that should be the answer of this question. Okay, right. So the next problem type is based on buoyancy. So a cube of ice float partially in water, partially in kerosene oil. The ratio of the volume of ice immersed in water to that in kerosene oil. So we have to find the ratio. So what we can say, let us say V1 volume of the cube is in kerosene oil and V2 volume is in water. So the fluid displaced by the cube or the kerosene displaced by the cube we can say is V1, and the water displaced by the cube is V2. So the buoyant force we can say will be density of the kerosene oil times V1 times G plus density of water times V2 times G. So that is buoyant force, and since it is in equilibrium, this buoyant force must be equals to the gravitational force, which will be density of ice times V1 plus V2 times G, right? Now from this, density of the kerosene is 0.8 and G will get cancelled out everywhere. And density of water is 1 gram per cc, and density of ice is given as 0.9. Now from this we can say V1 comes out to be equals to V2. So it means it is equally its volume, V1 is equals to V2, so it is displacing equal amount of volume for kerosene and water. So it should be 1:1. So option 1 is the right answer. A sphere of relative density sigma and the diameter capital D has a concentric cavity of diameter D. So there is a sphere and it has a concentric cavity of diameter D. This is capital D, outer diameter. Its relative density is sigma. The ratio of D by D if it just floats in water. So if it just floats in water, then we can say the buoyant force is balancing the gravitational force. Now in this case, the volume displaced or submerged volume will be 4 by 3 pi d by 2 cube, right? So that is the submerged volume. So the buoyant force will be density of water. So I'm taking it as 1 times the volume displaced 4 by 3 pi d by 2 cube times G. Now this should be equals to the gravitational force, which is Fg, and Fg will be density of this sphere. So that will be sigma. It is relative density since we have taken densities in grams per cc. So sigma is nothing but the density of sphere in CGS. So sigma times the volume of the material, that will be 4 by 3 pi d by 2 cube minus small d by 2 cube times G. Now we have to just remove the constant factor. So 4 by 3 pi will get cancelled out. G will get cancelled out. Okay, so and even this 2 will get cancelled out. So we have d cube is equals to sigma times d cube minus small d cube. Now from this we have to find d by small d. Let us divide with d cube, small d cube, right? So I'm taking d by d as x. So we have x cube is equals to sigma times x cube minus 1. So from this sigma minus 1 x cube will be equals to sigma. So x will be sigma upon sigma minus 1 raised to power 1 by 3. So option 2 is the Right answer. Okay, now the next concept is equation of continuity. So figure below shows the liquid being pushed out the tube by the piston having the area of cross section of 2 square centimeter. So here we have 2 square centimeter. The area of cross section at the outlet is 10 millimeter. So here we have 10 millimeter square. If the piston is pushed at a speed of 4 centimeters per second, the speed of the outgoing flow. So in according to equation of continuity, the flow rate doesn't change for an incompressible fluid. So area of cross section A1 V1, where V1 is the velocity, is equals to A2 V2. So we have to find V2. So A1 is 2 into 10 raised to power minus 4. V1 is given as 4 centimeters per second divided by A2 is given as 10 into 10 raised to power minus 6. So from this we are getting 80, right? 80 centimeters per second. So that is the answer. Right, so next question based on the same problem type, equation of continuity. Glycerin of density 1.25 into 10 raised to power 3 kilograms per meter cube is flowing through the conical section of pipe. The area of cross section, so we have given a conical section like this, right? At the left hand we have area of cross section 10 square centimeter, at the right hand we have 5 square centimeter. Pressure drops across its length is 3 Newton per meter square. So pressure drops, so P1, let's say here is P2, right? So pressure is more, if we have a horizontal pipe, so the pressure will be more uh, at the cross section where the speed is less. So speed will be less at the left cross section and speed will be more at the right cross section. So we can say P1 will be greater than P2. So we have to find the rate of flow of glycerin through the pipe. So first of all, here we have to apply Bernoulli's equation. So in case of a horizontal pipe, we can say P1 plus half rho V1 square is equals to P2 plus half rho V2 square. And P1 minus P2 is given to us, which is 3 Newton per meter square. So it will be half rho V2 square minus V1 square, right? Now we have this is our first equation, right? And the another equation, and how many unknowns we have? V1 and V2 both are unknown to us. Now another equation will be equation of continuity. So we can apply A1 V1 is equals to A2 V2, and A1 is 10, V1 is A2 is 5. So V2 comes out to be 2 times V1. And we want to find the flow rate. And A1 V1 is the flow rate, right? Volume flow rate. And A2 V2 is also flow rate. So let us find V1, right, from this equation. So we can write P1 minus T2 as 3. Half density is given as 1.25 into 10 raised to power 3. V2 can be written as 2 times V1, so we get 3 times V1 square. So 3 will get eliminated. So we are getting 2 divided by 1.25 into 10 raised to power 3, that is V1 square. So from this, we are getting 2 divided by 1250, or this is nothing but 625. So V1 will be 1 upon 25, right? So we got V1, which is 1 by 25 meters per second. So the flow rate will be A1 V1. So A1 is 10 into 10 raised to power minus 4, and V1 is 1 by 25. So, and we have to find answer in SI units only. So 1 by, so we can write this as 100 divided by 100. So that will be 4. So 4 into 10 raised to power minus 5. So the answer will be 4, right? So 4 is the answer of this question. Okay, the surface of water in a water tank of cross section area 750 square centimeter on the top of the house is H meter. The surface of water in water tank of cross sectional area on the top of the house is H meter, okay, above the tap level, okay. something like this is given to us. So that is the tap. And this is H. And this area is given as 750 square centimeter. The speed of water coming out through the tap of the cross-sectional area 500 square millimeter is 30 centimeters per second. So through this, the water which is coming out is having a speed of 30 centimeter per second. Area of cross section is also given, which is 500 square millimeter. At that instant, dH by dt is x into 10 raised to minus 3 meters per second, the value of x. So what is happening in this case? This level is going down and water is coming out, right? So we can apply equation of continuity between 1 and 2. So we can say A1 V1 is equals to A2 V2, and this dH by dt is nothing but the speed of the free surface, right? dH, the rate at which the h is decreasing, that is the speed of the free surface. So we have to find the speed. So A1 is 750 into 10 raised to power minus 4. V1 is nothing but dH by dt, and A2 is 500 into 10 raised to power minus 6, and V2 is 30 into 10 raised to power minus 2. So I've just converted everything in SI units, and dH by dt is x into 10 raised to minus 3. So let us simplify this. 0 will get cancelled out, so this will give us 25. Now this will give us 20. So dH by dt will be 20 into 10 raised to power minus 8 plus 4, and this is given as x into 10 raised to power minus 3. So this will be 2 into 10 raised to power minus 3 is equals to x into 10 raised to power minus 3. So x will be 2. So 2 is the answer of this question. Right, so the next question is based on Bernoulli's equation. A plane is in a level flight at a constant speed, and each of its two wings has an area of 40 square meter. If the speed of the air is 180 kilometers per hour over the lower wing surface and 252 kilometers per hour over the upper wing surface, the mass of the plane is, so what they are saying, let us say we have the wings. So this is a cross-sectional view of the plane. On the lower surface here, the speed is 180 kilometer per hour. At the top, it is 252 kilometer per hour. Each of its wing has an area of 40 square meter. So if you apply Bernoulli equation between 1 and 2, right? So at the, we can assume, we can ignore the thickness of the wing. So we can say 1 and 2 are at the same level. So if you apply Bernoulli, we can say P1 plus half rho V1 square is equals to P2 plus half rho V2 square. So we will get P1 minus P2 as half rho V2 square minus V1 square. Now that will give us the pressure difference between 1 and 2. And with this pressure difference, we can find the lift, or we can find the force exerted by the air in the upward direction, and that force will balance the weight of the plane. So let us calculate this. So 180 can be written as in meters per second, 5 by 18, so that will be 50 meters per second, and 256 into 5 by 18, so that will be 2, and this will be 2. So it will be 18. Okay, sorry, let me correct this. 252 is given, right? Not 256. Two, and this will be 28, right? And this will be 14, so this comes out to be 70 meters per second. So we can write this as half, and the air density is given as 1. V2 is 70 square minus 50 square. So we got the pressure difference. So half into 120 times 20. So 10, so this comes out to be 1200 Newton per meter square. So we got the pressure. So the lift force in the upward direction will be P1 minus P2 times the area. So the total area will be 2 times 40, because 40 is the area of one wing. So it comes out to be 1200 into 80. 16, 9. So 96000. So that is the force in the upward direction. So the weight will be, so that will be nothing but mg. And g is given as 10. So m will be 9600. So 9600 will be the answer. Okay, right. So let us see the next question. The reading of the pressure meter attached with a closed pipe is 4.5 into 10 raised per 4. On opening the valve, so basically what we have given, so there is a pipeline, and here we have given a valve, right? And there is a pressure meter here. Let us, this is the pressure meter which is telling us what is the pressure. On opening the valve, the water starts flowing. So earlier the water was not flowing, and in that instant the pressure is given as 4.5 into 10 raised per 4. On opening the valve, water starts flowing, and the reading of the pressure meter falls to 2 into 10 raised per 4. Right, so the velocity of water is found to be, so here what is happening, the drop in pressure will be nothing but the gain in kinetic energy, right? So the loss in, you can see, the pressure energy will be the gain in kinetic energy. So delta P will be 4.5 into 10 raised per 4 minus 2 into 10 raised per 4 is equals to half density, it's water, right? 10 raised per 3, and we have to find the velocity of water. So this will be 2.5 into 10 raised per 4 multiplied with 2 divided by 10 raised per 3 root of that. So this comes out to be, this will give us 10. So 25 times 2 root of that. So it comes out to be root 50, that is V, and they have said that the velocity is root of V. So basically this term is V, right? So V is 50. So 50 is the answer of this question. Right, so let us see this question. In the test experiment on a model aeroplane in wind tunnel, the flow speed on the upper and the lower surface of the wing is 70 and 65. If the wing area is itna, so we have done similar question. So it is based on this concept. So you can do this as a homework, right? If you try to solve this, you will get answer as 810, right? So try to solve this. Right, so the next question, statement 1, when speed of liquid is 0 everywhere, pressure difference at the 2 points depends on the equation P1 minus P2 is equals to rho GH2 minus H1. Yes, so this is the Bernoulli equation where we have equated V1 and V2 as 0. So this is correct. Statement 2, in a Venturi tube shown, 2GH is equals to V1 square minus V2 square. So 2GH. So basically in Venturi tube, it's a horizontal tube, so we can say P1 minus P2 will be equals to half rho V2 square minus V1 square. Now this P1 minus P2 is given is nothing but the pressure difference. So this will be rho GH. Right, so in this case statement 2 can be correct if this fluid which they are mentioned is of the is the same fluid, but it is not the same fluid. So in that case, so from this, if we let us say its density is rho naught, so half rho V2 square minus V1 square. So so this comes out to be 2 times rho naught by rho GH. Okay, so that should be so we have it is not v1 square minus, even if I consider same fluid, right? So it should be, if I consider same fluid, then it should be v2 square minus v1 square, not v1 square minus v2 square. So option statement 2 is incorrect. Statement 1 is correct. So statement 1 is correct, statement 2 is incorrect. So correct Bernoulli's equation. So we know that Bernoulli equation is P plus half rho V square plus rho GH is constant. So half rho V square rho G. So option 2 is the right answer, right? Okay, right. So another question based on Bernoulli's equation. An ideal fluid of density 800 kilograms per meter cube flows smoothly through a bent pipe that tapers in cross section of from A to A by 2. Pressure difference between the wide and the narrow section of the pipe is 4100 Pascal. At wider section, the velocity of the fluid. So we have to find V1, which is given as root x by 6. And we have to find the value of x. So here we can apply Bernoulli and equation of continuity. So if you apply equation of continuity, then A V1 will be equals to A2 by V2. So V2 comes out to be 2 times V1, right? And if we apply Bernoulli's equation between 1 and 2, so we can say P1 plus half rho V1 square plus, if I consider this as my reference level, then H1 will be 1 meter. So rho G 1 meter is equals to P2 plus half rho V2 square plus rho G 0, because the second cross section is at the reference level. So this will become 0. And density is given and pressure difference is also given, right? 4100. So P1 minus P2 is 4100. So 4100 is equals to plus rho g times 1, and its density is 800. So that will be 800 times 10 is equals to half 800 times V2 square minus V1 square. So V2 square can be written as 4V1 square minus V1 square. So the left hand side will be 8000 plus 4100. So that will be 8000 plus 4. So 12100 multiplied with 2 divided by 800. So this will be 3V1 square. Right. So let us simplify this. So this will get cancelled out. This will give us 4. So 121 by 12 root of that. Now, now root of 121 by 12 is given as root x by 6. Right. So 121 by 12 is times 36. That will be x. So that will be 3. So that will be 363. So x comes out to be 363. So that is the answer of this question. Right, so now let us see the next problem. The area of cross section of a large tank is 0.5 square meter. It has a narrow opening near the bottom, having the area of cross section 1 square centimeter. A load of 25 kilograms is applied on the water at the top in the tank, neglecting the speed of water in the tank. The velocity of the water coming out of the opening at the time when the height of the water level in the tank is 40 centimeter above the bottom will be. So we have to find the speed velocity of efflux in centimeters per second. So let me first draw the diagram. So here we have given a tank and there is a small opening at the bottom. And this level is at 40 centimeter from the bottom, and we are exerting a force with 125 kilogram mass. Right, and along with this 25 kilo mass, there will be a pressure exerted by the atmosphere. So let me call this point as 1 and this point as 2, and velocity is coming out with and water is coming out with the velocity v. So what we're going to do, we'll apply Bernoulli's equation between 1 and 2. Area of cross section at this wider section is given as 0.3 5 square meter, and at this orifice it is given as 1 square centimeter. So here we can apply A1 V1 is equals to A2 V2, but they have clearly mentioned that we don't have to consider speed of the water in the tank, so we cannot apply this. Now we can directly apply Bernoulli. So let us first find the pressure at 1. So pressure at 1 will be atmospheric pressure plus pressure due to the load, which will be mg by A, where A is the area of cross section. So atmospheric pressure is 10 raised power 5 and mass is 25, G is given as 10, area of cross section is given as 0.5. So that comes out to be 10 raised power 5 plus 500. Pressure at 2, just outside the orifice, pressure will be atmospheric. Now we can apply Bernoulli's equation. So P1 plus half rho V1 square, which term will be 0, plus rho GH. So if I consider orifice as my reference level, then H1 will be 40 centimeters, so 0.4 meters, equals to P2 plus half rho V2 square, let me call this as V2, plus rho G 0, because orifice is at the reference level. So this term is 0. P1 is 10 raised power 5 plus 500, and then rho G will be 10 raised power 4 times 0.4 is equals to half rho is 10 raised power 3 times V2 square, and P2 is 10 raised power 5. So 10 raised power 5 will get cancelled out. So we are getting 500 plus, so it comes out to be 4000 is equals to 500 V2 square. Now from this we are getting 9 is equals to V2 square. So V2 comes out to be 3 meters per second, and we have to find answer in centimeters per second. So it will be 300 centimeters per second. So 300 is the answer of this question. Right, in such type of questions, sometimes they will consider atmospheric pressure at P1, and sometimes they do not consider. So do check your answer with both the ways, and accordingly you can mark your options. A liquid of density 750 kilograms per meter cube flows smoothly through a horizontal pipe that tapers in a cross-sectional area from A1 to A2, where A2 is half of A1. The pressure difference between the wider and the narrow section of the pipe is 4500 pascals. The rate of flow. So here we have to find the rate of flow, which is volume flow rate in meter cube per second, and we know that it is the product of area of cross section and the velocity. So let me first draw the diagram. So here we have area of cross section A2, here we have area of cross section A1, here velocity is V1, here velocity is V2. So here first we can apply equation of continuity. So we can say A1 V1 is equals to A2 V2, and A1 is 2 times A2, so 2 V1. So V2 will be 2 times V1. Now we can apply Bernoulli's equation between 1 and 2. So P1 plus half rho V1 square, since it's a horizontal pipe, the H term will not come into picture, equals to P2 plus half rho V2 square. So from here P1 minus P2 will be equals to half rho V2 square minus V1 square, and P1 minus P2 is given as 4500 times 2 divided by the density. It's liquid, it has a density 750, and V2 can be written as 2 times V1, so it will become 3 times V1 square. So this will be 15 and this will be 90, or we can say 6, so it comes out to be 12 by 3, which is 4. So V1 square is 4, so V1 is equals to 2 meters per second. Now we got V1, A1 is also given, so the flow rate in meter cubes per second will be V1 times A1. V1 is 2, A1 is given as 1.2 into 10 raised to power minus 2. So that will be 2.4 into 10 raised to power minus 2, or we can write this as 2.24. times 10 raised to power minus 3 meter cube per second. So if we compare, the answer comes out to be 24, right? Right, so let us say the next question based on Bernoulli's. A fully loaded Boeing aircraft has a mass of 5.4 into 10 raised to power 5 kilograms. Its total wing area is 500 square meter. It is in level flight with the speed of 1080 kilometers per hour. The density of the air is 1.2 kilogram per meter cube. The fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface in percentage will be. So here what they're saying, if I draw the diagram, so let us say this is the left wing and this one is the right wing, and if I consider 2 points, let me call this point as 1, this point as 2. So the to provide lift, to have lift, in that case pressure velocity at 1 should be greater than velocity at 2. Only in that case, if velocity at 1 is greater, then pressure at 1 becomes lesser than the pressure at 2. So and density is given. Let us say velocity, and we have to find the fractional increase in the speed of the air on the upper and the lower. Okay, so what we can do, we can assume that the plane is steady, like the gravitational force is balanced by the upward lift by the pressure difference. So what we can do, P2 plus half rho V2 square should be equals to P1 plus half rho V1 square, and P2 minus P1 will be equals to half rho V1 square minus V2 square. Now P2 minus P1 we will get by equilibrium of the aircraft in the vertical direction. So we can say P2 minus P1 times the area of cross section, that will be 500. That should be equals to mg. M is given as 5.4 into 10 raised to power 5 multiplied with 10. So from this, P2 minus P1 will be 5.4 times 10 raised to power 6 divided by 500. So if I multiply this with 2 and divide by 2, so we are getting 10.8 into 10 raised to power 3. So that will be 10800. So we got the pressure difference. So 10800. Multiply this with 2 and the density is given as 1.2. So it comes out to be 900. So V1 square minus V2 square is 18,000. And we have to find the fractional increase. So it means, so we have to find V1 minus V2 divided by V2. So this times 100. So that what we have to calculate, right? Percentage. Where V2 will be 1080 kilometers per hour, which is times 5 by 18. So this will give us 2 and it will be 120. So this will give us 60. So it comes out to be 300 meters per second. Now we got V2 and we have to find the fractional increase. So I'm assuming that the increase in velocity is small. So what we can write, so V1 can be written as V2 plus delta V, right? Where delta V is nothing but V1 minus V2. So this we have to calculate. So V1 square minus V2 square. So this can be written as V2 plus delta V square minus V2 square. Now we can write this as, let us take V2 as common. So V2 square times 1 plus delta V by V2 raised to power 2 minus V2. Now we can use binomial approximation. So we can write this as V2 square times 1 plus 2 times delta V by V2 minus V2 square. Now 1 will get cancelled out. So we are getting 2 times V2. So 2 times V2 square times delta V by V2, and this we have to calculate, right? So 18,000 is equals to divided by 2 times V2 square, that will be delta V by V2. So it comes out to be 18,000 by 2 times V2 square, that will be 90,000. So that will be 10, this will be 2, and this will give us 1 by 10. So the fractional increase in the speed is 1 by 10. So the percentage will be 1 by 10 times 100. So it comes out to be 10%. So option 4 is the right answer. Right. So let us see the next question based on velocity of efflux. The water is filled up to height 12 meter in a tank having a vertical side wall. A hole is made in one of the wall at a depth h below the water level. The value of h for which the emerging stream of water strikes the ground at the maximum range. So here we have given a tank, and I'm assuming this tank is resting on the ground, and water level is given up to the height of 12 meters, and we have to find the depth at which the range of the ejected fluid is maximum. So let us say at a height h below the free surface, this range is maximum, and we know that in such case the range will be maximum when this h is half of this 12, right? So h will be 12 by 2, so that will be 6 meters. And if you want to do that, you can assume some unknown h, then the velocity of efflux will be root of 2gh, and we can use this formula if area of cross section of the tank is very large in comparison to area of the orifice. Now the range will be given as root of 2gh times the time taken by the fluid from point A to point B. So here we have to apply the concept of horizontal projection from the height, and the time will be root of 2h by g. Now from this we are getting, so this height will be 12 minus h, so it will be root of 2 times 12 minus h. So we are getting 2 times root of h times 12 minus h, and when you use maximum minima, you will get h as 6. For h equals to 6 meter, r is maximum, right? So answer will be 6. Okay, next concept is based on the thrust due to water. Here you have to remember that if the fluid is there is a pipe and fluid is coming out with a velocity v, and the area of cross section is a, and the density of the fluid is rho, then the force experienced by the pipe due to the ejected fluid will be rho a v square, right? So this expression you have to remember. A block of metal weighing 2 kilograms is resting on a frictionless plane. It is struck by a jet releasing water at a rate of 1 kilogram per second and a speed of 10 meters per second. Then the initial acceleration of the block, and another formula which you have to remember is the thrust can also be written as dm by dt times the v relative, right? Now in this particular case we have given dm by dt and we have given the speed, so the thrust will be 1 times 10, so that will be 10 newton. So this block is experiencing a thrust of 10 newton, and due to that thrust it will experience an acceleration of 10 by mass, which is mass is given as 2, so that will be 5 meters per second square. So option C is the right answer. Okay, let us see the next question based on the same concept. A pressure pump has a horizontal tube of cross-sectional area 10 square centimeter for the outflow of water at a speed of 20 meters per second. So there is a tube which is having an area of cross section 10 square centimeter, and the fluid is coming out with 20 meters per second. The force exerted on the vertical wall just in front of the tube, which stops water horizontally. So when it stops water horizontally flowing out of the tube, in that case the force experienced by the wall will be rho a v square, But suppose if we have given that the fluid is striking the wall and rebounds with the same velocity, in that case the force will be 2 rho a v square. So here we have to use rho a v square. So density of water is 10 raised per 3, area of cross section is 10 into 10 raised per minus 4, and v square will be 400. So it will give us 400 Newton. So option D is the right answer. Right, so let us see another question. A balloon has a mass of 10 grams in air. The air escapes from the balloon at a uniform rate of 4.5 centimeters per second. If the balloon shrinks in 5 seconds completely, then the average force exerted on the balloon will be. So the force exerted by the ejected air will be how much? So it will be dm by dt times v, where dm so the dm by dt is nothing but so the total air in the balloon is 10 grams, so we can say it will be 10 into 10 raised per minus 3, and the entire air comes out in 5 seconds, and we have to find the average force, right? So that's why I've taken the total mass and how much time it takes to come out. 5 seconds multiplied with 4.5 into 10 raised per minus 2. So that will be 0.9. So 9 into 10 raised per minus 5 Newton. And we know that 1 dyne is equals to 10 raised per minus 5 Newton. So that will be 9 dynes. So option B is the right answer. Right, so now let us see the next problem type based on surface tension. So statement 1, viscosity of gases is greater than that of the fluid. That is incorrect. Viscosity of like fluid is greater than the viscosity of liquid is greater than the viscosity of gas. Statement 2, surface tension of liquid decreases due to the presence of insoluble impurities. So what happens due to, so yes, so in this case when we add some impurities, surface tension decreases because of the change, you can say because of the change in the force. So here the adhesive force of the insoluble impurities will alter the surface tension, so it will decrease. So statement 2 is correct, statement 1 is incorrect, so it should be option 2, right? Right, let us see the next question. A drop of liquid of density rho is floating half immersed in a liquid of density sigma and surface tension 7.5 into 10 raised per minus 4 Newton per centimeter. The radius of the drop in centimeter will be. So here, let me first draw the diagram. So there is a drop. And it is half submerged. Liquid has a density sigma and the drop is having a density rho, right? Surface tension is given and we have to find the radius of the drop. So here what we can do, there will be a gravitational force, there will be a buoyant force, right? Apart from this, there will be a surface tension force on the periphery in the upper direction everywhere, right? Let me call this as Fs. So Fs will be 2 pi r times the surface tension. I am taking surface tension as S, and the gravitational force will be mg, where m is the mass of this drop, and it will be rho times 4 by 3 pi r cube times g, and F B will be density of the surrounding fluid times the volume submerged, which will be 2 by 3 pi r cube times g. Now it is in equilibrium, so we can say Fs plus Fb must be equals to Fg, right? So if surface tension is not given in the question, in such cases we can ignore the surface tension force and we can assume that the gravitational force is balancing the buoyant force. So this will be written, so it can be written as 2 pi r s plus sigma 2 by 3 pi r cube times g is equals to rho 4 by 3 pi r cube times g. So 2 pi r will get cancelled out. Right, so we get S is equals to r square by g by 3 times 2 rho minus sigma. And surface tension is given as 7.5 into 10 raised power minus 4 Newton per centimeter. So it will be 7.5 into 10 raised power minus 4 divided by 10 raised power minus 2 in SI units. And it will be r square and g is 10 by 3 times 2 rho minus sigma. So let us simplify this. So we are getting 22.5 into 10 raised power minus 3 divided by 2 rho minus sigma. So that will be r square. So radius we have to calculate, and we have to find radius in terms of SI units, right? So let me just take the square root. So it will become 225 into 10 raised per, we have to find in centimeter, right? First let us find in SI and then we can find in centimeters. Rho minus sigma, that will be r. So if you look at the option B and option C cannot be the answer. So let us check. So let us take the square root of this, right? So it will become 4. So square root of 225 will be 15 and times 10 raised per minus 2 divided by root of 2 rho minus sigma. And this will be in meters. So in centimeter it will be 15 upon root 2 rho minus sigma. So option A is the right answer. Right, so the next concept is surface energy. A big drop is formed by coalescing 1,000 small droplets of water. The surface energy will be. So we know that surface energy per unit surface area is surface tension, right? So we're going to use this concept. And if a big drop is formed by coalescing small drops, the total surface area will decrease and the surface energy will also decrease. So here what we can do, in such question we can conserve volume. So volume of big drop is equals to volume of 1,000 small drops. So if I assume the radius of the big drop as capital R and the radius of small drop as small r, so we can write it as 4 by 3 pi capital R cube is equals to 1,000 times 4 by 3 pi small r cube. So 4 by 3 pi will get cancelled out. So r comes out to be 10 times small r. Now we got the relation between the radii. Now we have to find the surface tension will become. So we have to find the surface tension of surface energy. Sorry, surface energy will become. So surface energy of the big drop we have to find. So let us say for the big drop, it will be surface tension times the area of the big drop, that will be 4 pi capital R square. So that is nothing but S times 4 pi 100 small r square. So that will be 400 pi r square times S, whereas the surface energy of one small drop, it will be S times 4 pi small r square, and if I multiply this with 1,000, we are getting 4,000 pi small r square times S. Right, so if you compare these two surface energies, it is getting 1/10. So option 4 is the right answer. A small liquid drop of radius r is divided into 27 identical liquid drops. If the surface tension is T, then the work done in the process. So when we divide a big drop into small drop, the surface area will increase. So there will be an increase in potential energy. So here we can say work done by the external agent will be increase in the potential energy. Right, so it will be U final minus U initial, and U final in this case is nothing but the surface tension times the increase in the surface area, or you can say surface tension times the surface area of 27 drops. So that will be 27 times 4 pi r square, right? And U initial is surface tension times 4 pi capital R square. Now we have to find the relation between small r square and the capital R square. So here we can conserve volume. So volume of big drop is equals to volume of 27 small drops. So 4 by 3 pi capital R cube is equals to 27 times 4 by 3 pi small r cube. So 4 by 3 pi will get cancelled out, so r comes out to be 3 times small r. So we can write final potential energy as T times 27 times 4 pi capital R by 3 square. So that will become T times 27 times 4 pi R square by 9. So that will give us 3. So let us substitute the values. So it will be 12 T pi capital R square minus 4T pi capital R square, so which comes out to be 8T pi capital R square. So option 1 is the right answer. Now let us see this question. A soap bubble is blown to a diameter of 7 centimeter, and 36,960 ergs of work is done in blowing it further. If the surface tension of the soap solution is 40 dyne per centimeter, then the new radius in centimeter will be. So we have to find the new radius. So let us say this is the bubble which is having a diameter 7 centimeter. Now we have increased the diameter. We are doing some work and we are able to increase the surface area. And so we are able to increase the diameter. And let us, the new radius is r. So, so the work done by the external agent will be increase in the surface energy, right? So this can be written as, so in soap bubble there are two surfaces, so we can write this as surface tension, say T is the surface tension, T times the surface area. Final surface area will be 2 times 4 pi r square minus initial potential energy will be T times 2 times 4 pi 7 by 2 square. So I am finding answer in terms of in CGS only. So from this 2T pi r square, or not 2T pi r square, work done is given. Let us substitute the value. So 36960 is equals to surface tension. So 2 times 4 pi times T will be common. So r square minus 7 by 2 square. And pi we have to take as 22 by 7. So it will be 36960 divided by 8 times 22 by 7. Surface tension is given as 40. R square minus 49 by 4. Now from this, let us divide this by 11. So this will be 3, and then we have 49, 4, and then we have 9, 6. So this will be 3, 30, sorry, it will be 3, not 4. 3360, and this will give us 420, and this will give us 21. So we got 21 times 7 by 4 plus 49 by 4 is equals to r square. So we have 147 plus 49 by 4 as r square, or we can write this as 1691 by 4. So from this r comes out to be 14 by 2, which is 7 centimeter. Yeah, so the radius will be 7 centimeter. So 7 is the answer of this question. Okay, large number of water drops each of radius r combines to have a drop of radius capital R. If the surface tension is T, the mechanical equivalent of heat is J. The rise in the heat energy per unit volume. Right, so let us try to solve this rise in the heat energy. So basically, a large drop of water, it a large number of drops. So we are combining large number of small drops and make a giant drop, right? So what happens in this case? The energy will release. Now that released energy is being used in heating up the large drop. So what we can do, loss in surface energy will be equals to gain in heat energy, right? So that what we have to apply. Now what is the loss in surface energy? So it will be surface energy of small drops, all small drops, minus surface energy of big drop. So it will be let us say there are n small drops, so n times 4 by 3 pi small r cube is equals to 4 by 3 pi capital R cube. So I'm just equating the volume of the drops, right? And 4 by 3 pi will get cancelled out. So from this n comes out to be capital R by small r cube. So we got number of drops. So capital R by small r cube times surface area of each drop, so 4 pi small r square, minus 4 pi capital R square, right? And we have to multiply this with surface tension also, right? Okay, and let us simplify this. So we are getting surface tension is there, 4 pi is there, and we have to find mechanical equivalent is also given, rise in the heat energy per unit volume. So let us divide this with volume. So that is the heat energy. Let me call this as delta H. Now if I divide this with volume, so volume can be written as 4 by 3 pi capital R cube, right? So from this we can eliminate 4 pi, right? So this will give us T R square will be common, and then we have R upon R, small r, minus 1 divided by R cube by 3. So this will get cancelled out. So we're getting 3T by R, R minus small r, minus 1. Okay, so if I multiply this r in 1 by if I multiply the 1 by r inside, so we'll get 3T 1 by small r minus 1 by capital R. And we have given mechanical equivalent of heat. So if you divide this with J, we'll get the heat energy per unit volume. So the answer will be 3T divided by J, 1 by R minus 1 by capital R. So the answer will be option 4, right? Right, so let us see the next concept, which is based on excess pressure. So pressure inside the soap bubble is greater than the pressure outside by an amount. So in case of a soap bubble, the pressure inside is greater than outside as 4s by r, where r is the radius of the bubble. So option 2 is the right answer. A liquid column of height 0.04 centimeter balances excess pressure of a soap bubble of a certain radius. If the density of the liquid is 8 into 10 raised by 3 kilograms per meter cube and the surface tension of the solution is 0.28 Newton per meter, then the diameter of the soap bubble is. So here we have given the excess pressure is equals to, it balances the column length, liquid column height, right, of 0.04. So we can say rho GH will be equals to 4S by R, where R is the radius of the soap bubble and we have to find the diameter. So let me multiply this with 2 and multiply 2 in the numerator. So this will become diameter. So diameter will be 8S upon rho GH. Let us substitute the values. S is 0.28. Density of liquid is given as 8 into 8000. G is 10. H is given as 4 into 10 raised per minus 4 meters. Right? So this will become 8 into 28 times 10 raised per minus 2 divided by 8 times 4 into 10 raised per 0. So this will get cancelled out. This will give us 7. So it comes out to be 7 into 10 raised per minus 2 meters, or we can say 7 centimeters. So 7 is the answer of this question. Okay, right. So now the question based on excess pressure. The excess pressure inside a soap bubble is thrice the excess pressure inside the second soap bubble. The ratio between the volume of the first and the second. So excess pressure, let us take the first bubble radius as R1 and for the second bubble radius as R2. So we can say 4S by R1 is 3 times 4S by R2. So from this we can say R2 is 3 times R1, right? We have this relation. We have to find the ratio of the volume. So V1 by V2 will be equals to 4 by 3 pi R1 cube by 4 by 3 pi R2 cube. So that will be R1 by R2 cube, and R1 by R2 is 1 by 3. So 1 by 3 cube. So that will be 1 by 27. So option 3 is the right answer. Another question based on excess pressure. There is an air bubble of radius 1 millimeter in a liquid of surface tension 0.075 Newton per meter, and density is 1000 kilograms per meter cube. At a depth of 10 centimeter below the free surface, the amount by which the pressure inside the bubble is greater than the atmospheric pressure. So there is a bubble, air bubble, at a depth of 10 centimeter, and let us say the atmospheric pressure is P0, and we want to find the pressure inside the bubble. Okay, difference of the pressure inside the bubble and the atmospheric pressure. So let us say the pressure inside the bubble is PA. So we have to find PA minus P0. Okay, right. So what you can do in case of a air bubble, the excess pressure is 2S by R. So if I consider a point outside B, so pressure at B will be P0 plus rho GH, and pressure at A will be greater than pressure at B by 2S by R. So pressure at A will be greater than pressure at B by 2S by R. So from this we can say PA minus P0 minus rho plus rho GH is equals to 2S by R. So here PA minus P0 will be 2S by R plus rho GH. So we have to find PA minus P0. So 2 times S is 75 into 10 raised per minus 3 divided by radius is given as 1 millimeter. So that will be 10 raised per minus 3, plus density is 10 raised per 3, G is 10, H is given as 10 centimeters. So that will be 0.1 or 1 by 10 meters. So this comes out to be 150 plus 1000, which will be 1150 Newton per meter square or pascals, right? So 1150 is the answer of this question. Right, let us the next question. A spherical soap bubble of radius 3 centimeter is formed inside another spherical bubble of radius 6 centimeter. So we have given us a bubble of radius 6 centimeter, and inside this bubble there is another bubble of radius 3 centimeter. Right? If the internal pressure of the smaller bubble, so at point A in the above system, is equals to the internal pressure of the another single bubble of radius r, the value of r will be. Okay, right. So first let us find the pressure at A, excess pressure at A. Let us say outside pressure is P naught. At B, pressure at B will be P naught plus 4s by 6 centimeter, right? Whereas pressure at A will be greater than pressure at B by 4s by 3 centimeter. Okay, so we can write this as pressure at A is equals to P naught plus 4s by 6 centimeter plus 4s by 3 centimeter. Okay, and now we have given that pressure at A, internal pressure of another soap bubble is same as A. So there is another soap bubble which has the same pressure as A, right? Pressure at A. So surrounding pressure is P naught. So PA minus P naught will be 4s by 6 centimeter plus 4s by 3 centimeter. Or we can write this as 4s by r. So from this we can say 1 by r will be 1 by 6 plus 1 by 3. So that will be 3 by 6, or we can say r will be 2 centimeter. So 2 is the answer of this question. Okay, so when two soap bubbles of radius A and B coalesce, where B is greater than A, the radius of curvature of the common surface. So here, so this is the first soap bubble and this one is the second, and let's say this is the common surface. This bubble has a radius of curvature B, this bubble has a radius of curvature A, and let's say this surface has a radius of curvature C. We have to find C. So if I take point A and point B, and let us say surrounding outside we have pressure P naught. So PA will be greater than P naught by 4s by B, whereas PB is greater than P naught by 4s by A, and the pressure on the concave side is greater than pressure on the convex side, right? So in this case pressure at B will be greater than pressure at A by 4s by C, right? So let us substitute PA and PB in this equation. So we have P naught plus 4s by B is equals to, so 4s by A, P naught plus 4s by B plus 4s by C. So P naught will get cancelled out, 4s will get cancelled out, so 1 by A minus 1 by B is equals to 1 by C. So from this, AB upon B minus A will be the radius of curvature of the common surface. So AB upon B minus. So option 1 is the right answer. Okay, now the next concept is based on contact angle. So here assertion is given as a cloth containing oil or grease stains can't be cleaned by water wash. So that is correct. That is a fact. Reason, because the angle of contact between the oil, grease and water is obtuse. So so if I consider water and oil and grease, so let us, this is oil and grease. Now this angle is obtuse. Let me redraw the diagram. So this angle, they are saying this angle is obtuse. Yes, so this will be obtuse and the light of the above situation. So that's why the wettability, So we are not able to remove grease. Greater the contact angle, lesser it will be difficult for water to clean grease. So we can say as a reason is also the correct justification for the assertion. So option A is the right answer. Now the next concept is based on capillarity. Statement 1, if a capillary tube is immersed first in cold water and then in hot water, the height of the capillary rise will be smaller in hot water. So first of all, we should know what is the formula of capillary rise. So H is given as 2s cos theta divided by rho gr. So uh, height raised is directly proportional to the surface tension. So when we heat up the water, the surface tension decreases, right? As S decreases, H should also decrease. So if a capillary tube is immersed first in cold water, then in hot water, the height of capillary rise will be smaller in hot water. Yes, it will be smaller because in hot water, S will be less. Statement 1 is correct. The capillary tube is immersed first in cold water and then in hot water. The height of capillary rise will be smaller in cold water. That is incorrect. In cold water, the surface tension will be more, so height should rise. It should be even more. So statement 1 is correct, statement 2 is incorrect. So option 3 is the right answer. Now again another question based on capillarity. The contact angle between the solid and the liquid is the property of the material of the solid and the liquid as well, right? So that is true because it depends upon the cohesive as well as the adhesive forces. So statement 2, the rise of the liquid in the capillary tube does not depends on the inner radius. So that is incorrect because H is 2s cos theta upon rho gr, where r is the radius of the capillary. So statement 1 is true, statement 2 is false. So option 1 is the right answer. Okay, another question based on capillarity. When a capillary tube is dipped in a liquid, the liquid neither rise nor fall in the capillary. The contact angle may be 0. So H is 2s cos theta by rho gr. If theta is 0, then cos 0 will be 1. So H will be non-zero. So statement 1 is incorrect. Statement 2, the contact angle between the solid and the liquid is the property of the material of the solid and the liquid. So that is true. So statement 2 is correct and statement 1 is false. So option 3 is the right answer. Another question based on capillarity. The height of the liquid column raised in a capillary tube of a certain radius when dipped in a liquid A vertically is 5 centimeter. If the tube is dipped in similar manner in another liquid B of the surface of surface tension and density double the value of the tube A, the height of the liquid column rise in the liquid B will be. Okay, so here H is 2s cos theta by rho gr. So the liquid is different, so S will be different, right? Surface tension and the density both are double, right? So here G will be same. No information is given about the contact angle, so I'm assuming contact angle is also same, right? So this is same, 2 is constant. Radius of the capillary is also same. I'm assuming this, right, because no information is given. So we can say H is directly proportional to S and inversely proportional to the density of the fluid. So here H2 by H1 will be S2 by S1 times rho 1 by rho 2. And we have given rho 2 is 2 times rho 1 and S2 is 2 times S1. So that will be 2 and this will be 1 by 2. So it comes out to be 1. So H2 will be nothing but H1 and H1 is given as 5 centimeter. And we have to 5 centimeter and we have to find answer in meters. So it will be 0.05 meters. So option 3 is the right answer. Okay, next concept is viscous force. The velocity of upper layer of water in a river is 36 km per hour. Shearing stress between the horizontal layers of water is 10 raised per minus 3 Newton per meter square. Depth of the river is how much? We have to find the depth of the river. Coefficient of viscosity of water is given as 10 raised per minus 2 Pascal second. So here if I consider this block of water, so there will be, let us say, a viscous force, and this viscous force will be given as A eta dV by dx, right? And this force upon area is nothing but the shear force. So eta times dV by dx will be the shear force, or shear, you can say shear stress. Eta is given as 10 raised power minus 2, and dV by dx can be written as velocity of the topmost layer divided by the depth. And the depth here, we have to calculate the depth. Let us say depth is d, and this will be stress. So let us substitute the values. So 10 raised power minus 2, velocity is given as 36 kilometers per hour. So 36 times 5 by 18, so that will be 10. So 10 by d, and the stress is given as 10 raised to power minus 3, right? So this will give us 10 raised to power minus 1. So d comes out to be 100 meters, right? So 100 is the answer of this question, right? Let us see this question. So assertion is given as product of pressure when and time has the same dimension as that of the coefficient of viscosity. So here eta is Fv divided by A dV by dx. Okay, so the unit of eta will be kilogram meter inverse second inverse, whereas unit of pressure times time, pressure is force upon area, so that will be kilogram meter second raised to power minus 2, force upon area will be meter square times the time, that is second. So this will give us kilogram meter inverse second inverse. Yes, assertion is correct. Both have same dimension, same unit. Coefficient of viscosity is force upon velocity gradient. Reason is incorrect, because coefficient of viscosity is force upon area. There has to be area in the denominator also, right? So reason is incorrect. So A is true, R is false. So C, option C is the right answer, right? Right. Another question based on viscous force. A metal block of base area 0.2 square meter is placed on a table as shown in the figure. A liquid film of thickness 0.25 millimeter is inserted between the block and the table. The block is pushed by a horizontal force of 0.1 Newton and moves with a constant speed. If the viscosity of the liquid is 5 into 10 raised to power minus 3 Poisson, and this is the SI unit, right? The speed of the block is right. So what you have to remember, 1 kilogram meter inverse second inverse is 1 Poisson, and this, if I convert this into CGS, so that will be 10 raised to power 3 into 10 raised to power minus 2 grams centimeters per second inverse. So this will be 10 grams centimeter inverse second inverse. Now this grams centimeter inverse second inverse is known as poise. So 10 poise. So 1 Poisson is equals to 10 poise. So that you have to remember, right? Where poise is the CGS, Poisson is the SI unit. Okay, right. So here we have given coefficient of viscosity in SI units. The speed of the block we have to calculate. So we are exerting a force on the block and it is moving with a constant velocity. It means the layer of the film is exerting a viscous force on the block in the opposite direction. So these two forces must be balancing. So we can see viscous force is nothing but 0.1 Newton, and it is given as A eta dV by dx, which dV by dx is the velocity gradient. Area of cross section is given as 0.2. Eta is given as 5 into 10 raised to power minus 3, and velocity is v, and dx in this case will be the thickness of the film. Thickness of the film is 0.25 millimeters, so 25 into 10 raised to power minus 5. Now from this, this will give us 5. So we have 0.1 divided by 0.2 times 5 times 10 raised to power minus 5 plus 3. So that will be the velocity. So 2.5 into 10 raised to power minus 2, or 25 into 10 raised to power minus 3 meters per second. So 25 is the answer of this question. Right, let us see the next question. Based on the terminal velocity, an air bubble of diameter 6 millimeter rises steadily through a solution of density 1750 kilograms per meter cube at a rate of 0.35 centimeters per second. The coefficient of viscosity of the solution is. So in case of a air bubble, terminal velocity is given as 2 by 9 r square g times the density of the solution divided by eta. Okay, so this is the terminal velocity and we have to find the coefficient of viscosity. So eta we have to calculate. So eta will be 2 by 9 r square g rho by vt. So 2 by 9, r is 6, diameter is 6 millimeters, so radius will be 3 millimeters. So 9 into 10 raised to power minus 6. G is 10, density is 1750, and terminal velocity is given as 35 into 10 raised to power minus 4 meters per second. So this will give us 5, and this will be 250. So this will be 50. 9 will get cancelled out. So we are getting 100 into 10 raised to power minus 6 plus 1 plus 4. So this comes out to be 10. So 10 Pascal second. So 10 is the answer of this question. Another question based on terminal velocity: a small spherical ball of radius r falling through the viscous medium of negligible density has a terminal velocity v. So if the surrounding fluid has a negligible density, right, so we can ignore buoyant force. Okay, another ball of the same mass but of the radius 2r falling through the same viscous medium will have a terminal velocity. Okay, so let us see. So if there is a ball which is falling through a viscous fluid, let us say v is the velocity, there will be a gravitational force in the downward direction and there will be a viscous force in the upward direction. Now this viscous force is given as 6 pi eta rv as per the Stokes law. So this gravitational force must be balancing the viscous force. So 6 pi eta rv must be equals to 4 by 3 pi r cube times g times the density of the ball. Let us take this density as sigma. Now from this we are getting this will be 2 and this will be 3. So v comes out to be 2 by 9 r square g sigma by eta, right? So we got the terminal velocity, and so terminal velocity is directly proportional to the square of the radius if we keep eta and sigma constant. Now what we have done, another ball of the same mass, so mass is same, so m1 is equals to m2. So we can say density, let me call this as sigma 1, right? Sigma 1 times 4 by 3 pi r cube is equals to sigma 2 times 4 by 3 pi 2 r cube. Now from this, sigma 1 will be 4 times sigma 2. So we can say v2 will be 2 by 9 2r square g 4 times so sigma 2 will be sigma 1 by 4 by eta. So this will be 2 by 9 r square g sigma 1 by eta times 4 by 4, so which is nothing but v1. So there will be no change, or sorry, let me check. 2 4 and this will be same mass, right? Sorry, this should be 8, not 4. Sorry, this should be 8. So here we have 8. So this will give us 2. So that comes out to be v by 2, right? So option 1 is the right answer. Right, so let us see the next concept. A small ball of mass m and density rho is dropped in a viscous liquid of density rho naught. After some time, the ball velocity will become constant. The viscous force on the body. So there will be a gravitational force mg, and there will be a buoyant force, and there will be a viscous force. So we can say viscous force will be mg minus fb, and this buoyant force will be uh, density of the surrounding fluid times the volume displaced times g, and volume of the body can be written as mass upon density. So this can be written as rho naught times mg by rho. So let us substitute the value. So mg minus mg times rho naught by rho. So that will be mg1 minus rho naught by rho. So option 4 is the right answer. Small water droplets of radius 0.01 millimeter are formed in the upper atmosphere and falling with a terminal velocity of 10 centimeters per second. Due to the condensation, if 8 such drops are coalesced and forms a bigger drop, the new terminal velocity. So here we can conserve volume. So volume of 8 small drops is equals to volume of big drop, right? So 8 times 4 pi r, radius is given as 1 into 10 raised per minus 5 meter, and this will be equals to 4 by 3 pi r cube. 4 by 3 pi capital R cube. So 4 by 3 pi will get cancelled out. So R comes out to be 2 times 10 raised per minus 5 meters. So we got the radius of the big drop, and we need to find the terminal velocity. And we know that terminal velocity is directly proportional to the square of the radius. So V2 by V1 is equals to R square by small r square. And so capital R is 2 into 10 raised per minus 5, small r is 1 into 10 raised per minus 5, square of that, so that will be 4. So V2 will be 4 times V1. V1 is given as 10 centimeters, so that will be 40 centimeter, right? 40 centimeter per second. So this should be 40 centimeters per second. Next question. A spherical ball of radius 10 raised per minus 4 meter, density 10 raised per 5 kilogram per meter cube falls freely under gravity through a height h before entering a tank of water. If after entering in water the velocity of the ball does not change, then the value of h is approximately. So it means the velocity just before hitting the water surface, that velocity will be root of 2gh, and then that velocity is nothing but the terminal velocity. Okay, so in this case we are dropping a ball from the height. So just before hitting the water surface, this velocity will be root of 2gh, and in water it starts moving with the terminal velocity. So here root of 2gh will be equals to vt. So let us substitute the value. So vt will be 2 by 9 r square g sigma divided by eta, right? So that will be 2 by 9, r will be 10 raised per minus r square will be 10 raised per minus 8, g is 9.8, sigma is 10 raised per 5, and eta is given as 9.8 into 10 raised per minus 6. So 9.8 will get cancelled out, so this comes out to be 2 by 9 into 10 raised per minus 3 plus 6, so that will be 2000 by 9, right? So so this is nothing but root of 2gh. So let us square. So it will be 4 into 10 raised per 6 divided by 81 divided by 2 times 9.8. So if you look at the options, option 1 and 3 are quite close, right? So let us use some approximation. Let us first find the answer. Okay, right, let us find this. So we are getting, so this will give us 2, and this will give us 4.9. So we have 81 times 4.9 inverse of that times 10 raised to power 6. So we are getting 2519, right? So it will give us 2519 meters. So the closest answer will be option number 2. Okay, let us see this question. A small steel ball is dropped into a long cylinder containing glycerin. Which of one of the following is correct representation of the velocity time graph? So when we release a steel ball, its velocity will increase, and after some time it will attain a terminal velocity. So it can't be the right answer. Here it is saying the velocity is increasing linearly, whereas the acceleration is not constant. Here they're saying the velocity is constant initially, which is incorrect. So option 2 is the right answer, because after some time it will attain terminal velocity, right? So that will be the terminal velocity. A small ball of mass m and density rho is dropped in a viscous liquid of density rho naught. After some time, the ball falls with a constant velocity. What is the viscous force? We have done same question, right? So I'm keeping this as a homework. So if you try to solve, you will get option 1 as the answer. Terminal velocity Vt of a spherical raindrop depends on the radius of the raindrop. So we know that terminal velocity is directly proportional to square of the radius. So option C is the right answer. A water drop of radius 1 micrometer falls into a situation where a effect of buoyant force is negligible. Coefficient of viscosity of air is 1.8 into 10 raised to minus 5 Newton second per meter square, and its density is negligible as compared to the water, which is 10 raised to 6 grams per meter cube. The terminal velocity of water drop is, so 2 by 9 r square g density by eta, right? So we have to substitute the value. So 2 by 9, r is given as 1 micrometer, so 10 raised to power minus 12, square of that. G is 10, density is 10 raised to power 3, and eta is 1.8 into 10 raised to power minus 5. Okay, so this will give us 0.9. So we have 1 upon 8.1 into 10 raised to power minus 12 plus 4 plus 5. So minus 3. Okay, right. So we're getting, we have to find answer 1 by 8. So 1 by 8 will be nearly equals to 0.123, right? Something like this, into 10 raised to power minus 3. Or we can write this as 123 into 10 raised to power minus 6. So option D is the right answer. The velocity of a small ball of mass 0.3 grams and density 8 grams per cc when dropped in a container filled with glycerin becomes constant after some time. If the density of the glycerin is 1.3 grams per cc, then the value of the viscous force acting on the ball will be x into 10 raised to power minus 4. The value of x is, so we have to find the viscous force, right? So the viscous force, when it starts moving with the constant velocity, viscous force will be equals to Fg minus, so here the velocity of the small ball is itna and density is 8 grams. So the density of the ball is 8 gram and it is falling in a less dense fluid, right? So Fg minus Fb will be the viscous force. So it will be 4 by 3 pi, okay, mass is given, right? So this will become mg minus mg rho by rho naught, right? Where this is the density of the liquid or the fluid, glycerin, and this is the density of the body, right? So it will become mg 1 minus rho by rho naught. So m, so 0.3 into 10 raised to power minus 3 times g is 10, 1 minus 1.3 divided by 8. So that will be 3 into 10 raised to power minus 3, 8 minus 1.3 by 8, and this will become 3 by 8 into 10 raised to power minus 3, and it will be 6.7. Okay, so approximate answer, let us find that. So 3 times 6.7 divided by 8, so it comes out to be 2.512 into 10 raised to power minus 3, or we can write this as 25.1 into 10 raised to power minus 4, and it's an integer type question, so answer will be 25, right? Now let us see the next concept, which is based on Reynolds number. So Reynolds number is a dimensionless number, and if you find this number, we'll get the type of flow, right? So it is given as rho dv by eta, where let us see what do we have. So if suppose there is a pipe of diameter d and the fluid is flowing with the velocity v, and this fluid has a density rho and the coefficient of viscosity eta, then we can define a dimensionless number. So this is dimensionless, and based on the value of this dimensionless number, the flow, we can categorize the flow as streamlined, turbulent, or unsteady. So as per NCERT, so different like literatures have different values. So as per NCERT, if R is less than 1000, then the flow will be streamlined. If R is greater than 1000 and less than 2000, it will be unsteady. When R is greater than 2000, then it will be turbulent, right? So that you have to remember. So the answer of this question will be rho Vd by eta. Now let us see this question, which is based on Reynolds number. What will be the nature of the flow of water from a circular tap when it flows flow rate increased from 0.18 liter per minute to 0.48 liters per minute? The radius of the tap and the viscosity of the water are 0.5 centimeters and 10 raised per minus 3 Pascal seconds. Density is given as 10 raised per 3 kilograms per meter cube. So here, first of all, the formula of Reynolds number is rho Vd by eta. So we have given density, diameter is given, coefficient of viscosity is given, and velocity we can calculate from flow rate, right? So the flow rate is area of cross section times the velocity. So velocity will be flow rate divided by area of cross section, and area of cross section is pi r square, where radius is also given. Okay, so let us first calculate the velocity in both the cases. So v1 will be 0.18 liters per minute. So liters per minute can be written as 10 raised per minus 3 divided by 60 meter cube per second divided by pi r square. So r is 0.5 centimeters, so it will become 25 into 10 raised to per minus 4. So 25, okay, right, so 10 raised to minus 6, sorry. So that will become 10 raised to power minus 6. 10 raised to power minus 3, yeah, minus 6. So if we simplify this, this will become 3 by 10 into 10 raised to power minus 5 divided by 25 pi into 10 raised to power minus 6. So that will become 3 upon 25 pi 10. So that is the velocity, right? Similarly, V2 by V1 will be, everything is same, only the flow rate is changing, right? So V2 by V1 will be 0.48 upon 0.18. That will be 8 by 3. So V2 will be 8 by 3 times V1. That will be 3 upon 25 pi, which will be 8 by 25 pi. So we got the velocities, right? So we can say R1 will be rho, that will be 10 raised to 3. Velocity will be 3 upon 25 pi times diameter is 1 centimeter 10 raised to minus 2 divided by eta will be 10 raised to minus 3. Okay, so this comes out to be how much? So let us simplify this. So it will be 30 upon 25 pi times 1000. Okay, so we got 30,000 upon 25 pi. So this comes out to be 382, right? So this number comes out with 382. And R2 by R1, it depends only upon the velocity because rest of the things are same, right? So it will be V2 by V1 V2 is 8 upon 25 pi, V1 is 3 upon 25 pi, so that will be 8 by 3. So R2 will be 382 times 8 by 3, so this will be 1 2 7. So this number is greater than 1000, right? So when the number is great, when R2 is when Reynolds number is greater than 1000, the flow will be unsteady, and this is less than 1000, so the flow is streamline. So we can say the steady flow to unsteady, right? So option 4 is the right answer. So here I conclude this video. So I have covered all possible types which can be asked in JEE Mains 2025. So wish you all the best for your JEE Mains. Thank you. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.